We're going to start our module 3, which focuses on machine learning and a very important application of machine learning in remote sensing for supervised classification. We're going to cover machine learning from the very basics, so you understand in what cases machine learning is recommended over the traditional approaches, what are the things you should worry about when you're using machine learning, and what are the best practices in using machine learning for remote sensing. So we're going to cover some theory, and then we're going to dive in and implement the whole supervised classification workflow in Earth Engine. So why do we want to use machine learning? Well, one reason could be that it's cool. Maybe your supervisor asked you to use machine learning, or maybe somebody who's funding your work says you have to use AI, and then only you'll get your funding. Maybe there are good reasons to do this, but the real reason to use machine learning is because machine learning is ideal for a lot of problems in remote sensing. Most problems in remote sensing boil down to detecting what are you looking at the image. So you have an image, you want to know, what am I looking at? What kind of material is this? Is this vegetation? Is it water? So it's detecting land cover type, or it's detecting, what am I looking at? Is it a car? Is it a house? Is it a road? And those kind of problems are well suited for machine learning, because if you have a perfect data set, for example, you say, I want to detect water. You go to the field, you measure the reflectance of water using a spectroscope and say, I know exactly how this water reflects sunlight and in different wavelengths. I take my satellite image and I'll find those wavelengths and say, this pixel has this reflectance in this wavelength, and now I've found my water. If everything was perfect, this would work. But all the Earth observation data has a lot of noise, because the satellite is up in the space 600 plus kilometers away. It is looking at something which is very far away. There's a whole atmosphere in between, and there's sensor noise, and that means the reflectance you measure will have some noise. So if the real reflectance was, say, 0.35, you may get 0.34. Tomorrow, the same place, you might get 0.36. So there's noise in the data, and that means you can't use your equations, your formulas. They're not robust enough against this noise. So if you want to figure out how can I determine different rules to separate out different materials based on the reflectances, that becomes a very hard problem because of the noise, because Earth observation data also has many spectral bands, and building rules for all of those becomes quite challenging. Instead, machine learning says, if you have some data, if you have some ground truth, you don't need to really figure out all the rules and all the formulas. We'll figure out using machine learning. We'll figure out what combination of bands will work to identify this particular object. So machine learning is ideally suited for remote sensing because we have lots of data, and instead of figuring out how to work with this noisy data and what are the rules, you can just say, I give you some ground truth data. You can figure out what are the rules governing how the objects are detected. There are two classes of machine learning algorithms that you can use. One is supervised and unsupervised. Unsupervised learning is where you just give the data to the algorithm. You say, here's my data, go figure out something. And this sounds interesting where you say, I don't need to do any work. I have my satellite images. I'll just give it to this algorithm and I'll get something back. Well, what you get back from unsupervised algorithms are clusters. They'll say, I don't know what I'm looking at, but I can find similar things. If you give it an image, it says, here is 4 different groups of pixels I found. Each group has similar reflectances. I don't know what each group is, but I found 4 different groups. So these are known as clustering algorithms. So once you get the clusters, it's the job of the analyst or maybe another algorithm to label those. So unsupervised algorithms will identify groups of pixels which are similar, and then you can manually label them or use another algorithm to label those. If you've heard of these algorithms such as k-means clustering, SNCC, those are the unsupervised algorithms. Most folks use supervised learning instead of unsupervised because you really want to know what you're looking at. So unsupervised learning doesn't require any human input beforehand. Supervised learning does require input in terms of training data. You need to label certain pixels and say, I know this pixel is vegetation. I know this pixel is water. And now go and find similar pixels. And the algorithm will go and find that. So you need a bit of training data to train your algorithm. Things such as linear regression, random forest, all are supervised algorithms that you can apply. We'll be focusing most of our module on supervised learning because that is what is most commonly used. Many people also use unsupervised learning as a starting point, and then they label the clusters. So instead of labeling the pixels first, You do unsupervised clustering, and then you label the clusters. And this is also known as object-based classification. So some of you would have read some research papers and say, oh, we use object-based classification. And that is doing unsupervised learning first, and then taking the results and doing supervised learning on that. In practice, most people end up using supervised learning, where they use supervised learning to classify the data, and then they use unsupervised learning to remove noise, to post-process the data. And that's the approach I recommend, and this will be teaching you this. So we'll cover both in a way, but we'll start with supervised learning. We'll classify our images. Once we are done, we can use unsupervised learning to post-process the data. But those algorithms are available in Earth Engine. If you want to do object-based classification, that scripts are also available. Before we dive in further into machine learning, I want to just briefly tell you that machine learning by itself is not better than any other system. So do not think that I'm using machine learning, my results will be better. The traditional way of solving a problem is known as expert system, where you define the rules of how you want to detect certain objects by using some indices, by using some formulas, by using the physical characteristics of the material, and then you can build a system that can identify objects. And those are known as expert system. These systems are great because you know exactly how the system works. You say, I detected this pixel as water because of this formula. I have the formula, I applied it, and I have my result. So they are easily explainable. It works fine for a small number of parameters. You can say I have 10 bands, I'll figure out the formula using those 10 bands, and I'll detect some object using that. But if I give you 500 bands, it becomes very hard to figure out the rules. So if you have a small number of parameters, which is bands in case of remote sensing, and you want to build a system, expert system is a good choice for those. Whereas machine learning, you don't really define the rules by hand. You just say, I don't know what are the rules to detect this particular object or this particular material. All I have is some input data and some labels. I have labeled this and said, this is water, this is vegetation. I don't know what combination of those input bands will allow you to detect that. Here's my data, here's the labels. Go and figure out what are the rules. So you start with data, you get rules. Expert system, you start with rules and you have a system. Inherently, neither of the system is better than the other. It really depends on your use case. Even all of the advances in machine learning and deep learning so far, the best data currently to detect water from Landsat images is a data set called global surface water. It's a global data set that detects water from Landsat images. None of the machine learning, it's an expert system. So you can see they've developed equations to detect water from Landsat images. That system outperforms any machine learning or deep learning system currently at the global scale. So again, machine learning is not better than expert system inherently. It just does different things. When people ask me that I want to use machine learning, I said, sure, it's going to solve some problems, but you're going to have different problems. It's not that it's going to solve all the problems. It's just the problems you deal with when you do machine learning are different. It's about collecting training data, cleaning training data, and tuning your models, versus in expert system, you will spend a lot more time understanding the problem and developing those equations. So again, consider both when you're working on a problem. Some problems are well suited for expert system, some are better suited for machine learning, and we'll go through some of the problem set space that is suitable for machine learning, and you will get a flavor of how to apply that to remote sensing. We'll learn about supervised classification in Earth Engine, because most problems in remote sensing, if you think about it, they boil down to doing supervised classification. Unless you understand what is going on, you cannot do any analysis. So classification is turning pixels into some labels. So I have pixels, human eyes can interpret some of them, but if you want to quantify them, you need to know what is each pixel. So you take your reflectance values and turn them into land cover classes, essentially taking an image like this. So this is a satellite image. You can make out some of those things, but let's say I want to answer the question, what is the tree cover in the city? Or I want to detect all buildings. And that means I need to know which pixels are buildings, which pixels are water, which pixels are vegetation, and so on. Right? So I need to turn this image into a classified image like this. So when you classify it, you get an image where each pixel has a label attached to it. And now quantified, you can now answer questions like, I want to know what is the tree cover in the city. Well, it just compute the area for the vegetation pixels. Right? I want to extract all the built up areas. Well, you have already labeled them, you can compute the area of those. Right? So supervised classification is essentially turning images like this into classified images like this. And once you have this, you'll be able to answer a lot of questions. Classification will help you answer the question, what does the pixel represent. Even if you know what kind of pixel it represents, let's say it's vegetation, you want to know what kind of vegetation. Is it agriculture? Is it forest? So you can kind of refine your classification and say, this is this kind of agriculture, or this is this kind of crop. And again, most of the problems will boil down to figuring out what those pixels are. If you want to do any quantification, what is it? How much area has changed? How much urban expansion has happened? First, you need to know which pixels are urban, and then you can say it was, urban X amount in last year, it's currently Y, and then you can compute the difference. Any change detection will also require you to know what you're looking at, and then only you can do the changes. So again, if you think about all the problems that you're working on, ultimately they'll boil down to detecting what's in the image, and that is the class of problems called supervised classification. And that's why it's one of the most important things to learn when you are working with Earth Engine and remote sensing, to know how to work with this and how to implement this so you can identify whatever objects you're trying to detect. This is the typical workflow of implementing supervised classification. You start with an input image, you collect some training data, you train a classifier, you classify the image, and you have the classified image. This is the workflow that you'll follow. We'll learn how to do this in Earth Engine. You can collect training data by visiting the ground and figuring out what is there on the ground, or you can look at the images on your computer and label them manually. Either way, you have to label some pixels and say, this is my input data. I've labeled them, train a classifier, and classify the image. Once you have the classified image, you can do visual assessment and say, this image looks okay. Or you can do some quantitative assessment. You'll get some numbers saying that how good is your classification result. It's 70% accurate, 80% accurate, and so on. If you're happy with the results, you can stop. If you're not happy with the result, you can further improve it. You can take the model that you've chosen, the classifier that you've chosen, tune some parameters, and check the accuracy, see if it improves. You keep doing that till you're happy with accuracy. If you're still not happy with accuracy, you can go and collect more training data or clean up your input data. So training data is really important in machine learning. Most of the time you're spending in collecting and cleaning your data. So you'll have to look at why my model is giving low accuracy. Maybe my input data is bad. You go and clean up your data, or you collect more training data, and you keep doing this till you're happy. So it's a cyclical process. You do this. Once you're happy with the output, you do some post-processing, smooth the results, remove the salt, pepper noise, and you have a final product. And we'll be implementing the whole workflow in Earth Engine. A lot of the machine learning stuff requires you to choose what algorithm you use, and each algorithm does something differently. In Earth Engine, it's just a matter of, say I'll choose this classifier and you write some code, it works. It helps to understand how the algorithms work so you can make more informed choices on which algorithm to use for which cases. So I'm going to explain a bit of theory about how different models work using the simple problem of water classification. So we'll step back and say, we'll do a multi-class classification in practice. But to understand, let's just say we want to take our image and just do a two-class classification. I want to take an image and just detect water. So I want to classify each pixel into water versus not water. And two parameters are useful because it's a 2D representation. I can show this on charts. I don't have a way to show charts in 12 dimensions. So it's easy to just work with just two parameters and say, if you have two classes, how does the model work internally? And they'll help you understand which model performs best on your input data. So let's say I want to take this image and classify into water versus non-water. How do I design my system? First, I need some training samples. In this thing, I need to know some pixels, maybe say 50 pixels or 100 pixels, which are water, 50 pixels, which are not water. So I'll go and collect that either by visiting the field. If it's easy for me to look at the image and understand what this pixel is, I can just label them using my computer. In case of water, it might be pretty obvious. I can just zoom in to the image and just say this is water. In case of crops, it might be harder. If you're trying to detect, say, coffee versus non-coffee, or trying to do wheat, it might be very difficult for you to say, oh, this farm is growing this crop. In that case, you may have to visit the farm and say, I have my GPS receiver, I'm standing here, and this pixel is this crop. So you have to go and collect the training data. Let's say in this case, I'll select some points and say I'll label each point, whether this is water or not water. And I have 100 points. I have 50 points, which I've labeled water, 50 points, which I've labeled not water. And I want to build a model. So I want to first extract the reflectances at those pixels. At each point, we have labeled just water, not water. We'll extract all the input reflectances, and that will be the input to our model saying, given this reflectances, go and figure out whether this is water or not water. Again, for simplicity's sake, we're just using two input bands. In practice, you'll use all the bands that are available to you. Here, just say, let's say we'll just use green and NR band and we extract the reflectances. And we generate a table like this. We have a table where there are 100 points, 100 rows, 2 columns of the reflectances in green and NIR band. And then I have my labels. I said, this is what you need to predict. So the model's job is to say, for each point, given a green and NIR reflectance, this is water. So build a model that can predict. I give you these 2 numbers, go and predict that it's water. If I give you these 2 different numbers, you should predict it's snow. So that's the job of the model. Most machine learning algorithms will require to generate a table like this. Whatever data set you're working this, whether it's temporal data, spatial data, non-spatial data, you have to generate a table where you have samples. For each sample, you have some input parameters that you want model to learn from, and an output parameter which the model has to predict. And once you have the table, you can use a machine learning algorithm. If I plot this on a chart, it looks like this. On the x-axis is a green band reflectance, y-axis is the NIR band reflectance, and the ones in blue are labeled as water, and ones in gray are not water. To the human eye, you can kind of see where the water is clustering, right? If I say, can you, in your mind, can you build a model to detect water? You can say, yeah, everything in this corner is water. But how does a machine determine this? How does computer know how to build a model to separate water from not water? And a model that can now work with the rest of the pixels. Remember, I need to classify the entire image. I have only information about 100 pixels. I need to go and figure out what are the value of other pixels, what classes they belong to. So given this data, we can use different algorithms, and they will all do things differently. They'll build different models to figure out which pixels are water versus non-water. We'll focus on these 3 algorithms. One is called SVM, classical machine learning algorithm, quite popular in remote sensing maybe 10 years ago. SVM is great for kind of single class, so water versus non-water. People used to use SVM a lot. In modern times, most people use some decision tree-based algorithms like Forest, which is a decision tree-based algorithm. And again, you have neural networks, which can also put non-linear model to your data. So we learn saying, if we give the same data to these different models, how will they go and build a model and predict what is the class of the pixel? SVM is an algorithm that is ideal for 2 classes. So if you just have 2 classes, forest versus non-forest, coffee versus non-coffee, if you have a problem like this, SVM works well. And what it does is it just figures out the line that separates water versus non-water. In 2-dimensional, it'll be line. In 3-dimensional, it'll be a plane. So if you think about 3-dimensional, you say, can I figure out, hold a piece of paper and fit it so that all the water points are below, all the non-water points are above. So you just figure out how to fit that plane or a line to your data so that it separates those 2 classes. If we give this data to SVM and say, all I have is labeled data, go and build your model. You'll work through the data, and the output of SVM will be a line like this. That's your trained SVM model. And once you have this line, you can say, my model is trained. Now I want to predict it. So you'll take this model and say, now go and predict what is the class of each pixel in my image. You'll go through each pixel. Let's say this first pixel, which is not yet classified. You'll go and say, what is the reflectance of green band here? What is the reflectance of NIR band? If the point falls here, it says this is below the line, it's water. If the next pixel is here, it says my next pixel is here, it's above the line, it's not water. And it'll do this for every pixel of the image, and you have a classified image. Quite simple model and works quite well for 2 classes. SVM was quite popular. Even today, some people use it, but over time, there was a new algorithm that was developed, which uses something called a decision tree, which is currently the most popular machine learning algorithm used in remote sensing problems because it's ideal for multi-class problems. And most of our problems are multi-class. You want to classify the image into water, agriculture, forest, urban, and so on. It can work with multiple classes. It's also very explainable. Once you train the model, you'll get a flowchart. It'll build a decision tree to say, how do I go and figure out what this pixel is? And you can kind of see that decision tree, and you can kind of understand how the model worked. It's currently the most popular algorithm because it's easy to interpret. Those flowcharts, it's simple. It can also do regressions. Many times you don't want to classify the pixel. You want to predict some numeric value. I want to build a model that can predict the crop yield. So I have some input parameter. Instead of predicting whether it's crop or not, I say how much yield will be for this particular pixel. And that's, want to predict some numeric value. Decision trees can also do that. Let's see how this works. Same data, remember those 100 labeled points. If we give it to a decision tree, it might go and build a flow chart like this. So I'll say, take my input pixel, check the reflectance of green band, whether it's less than X or more than X. Now, the key thing to understand is this X value. What is this threshold of X is figured out by the model based on the data. You don't have to give this as input. You just say, this is my data. When the model is training, it'll say, what is the right value for this X for me to check? Once it's figured out X, it says, check if the value is less than X or greater than X. If it's greater than X, check the NIR value. If the NIR value is less than Y or greater than Y. If it's greater than Y, it's not water. If it's less than Y, it's water, and so on. When you train a decision tree on your data, you'll get a flow chart like this. Now, when you want to predict, you say, I have a pixel whose reflectance is this much in green band, this much in NIR band. It's here. You'll ask the flow chart, what is this pixel? The flow chart will say, is the green greater than X or less than X? We say, okay, this part is greater than X. So I'll come here and say, check the Y value. Is it greater than Y or less than Y? And you say, oh, it's greater than Y. And then you say it's water. It's not water. And you'll do this for every pixel. You'll check this flow chart and figure out what is the class of each pixel. Since we have multiple bands and multiple parameters, this flow chart will look a little more complicated, but essentially this is what it does. In Earth Engine, when you train a decision tree, you will actually be able to see this tree that got trained. And I'll show you how that looks. And it'll do this for every pixel, and then you have each pixel that is classified. So this is great. It works better. It's explainable, but there is one problem. If you have a decision tree and you train one decision tree on a data, the decision tree algorithms will try to fit to your training data in a very exact way. So for example, let me say, in your training data, and we just learned that Earth observation data is noisy. Let's say I have one pixel whose value is like this. It's a water pixel, which I've labeled as water, but the reflectance is here. It's very high on green band and NIR band, most likely due to some noise in the data. I don't want my model to learn this. I want my model to ignore this, because I want my model to learn that all the water pixels are usually here. This is noise. But when you train a decision tree, the decision tree will say, okay, this is my training data. I'm going to go and build a model that will say, I'll figure out one more threshold here. I'll say, I have one more branch here. Check if it's greater than Z or less than Z. If it's greater than Z, check here. There'll be another parameter, W. And if it's greater than W, then it's water. Otherwise, it's not water. So it'll build a more unnecessarily complex tree to just try to fit this one data point. And you'll get this tree, which when it's trying to predict, any point that belongs here will be classified as not water, which is wrong. So the model, this is called overfitting in machine learning, where you are not learning from the pattern. You're just trying to replicate or mimic the input data, which might be noisy. So what you want is your model to be like a good student, not somebody who memorizes the input and just replicates this in output. You want the model to really understand the pattern and figure out and ignore the noise. So one solution that people came up was this algorithm called random forest. So this algorithm, instead of taking just one decision tree, it says maybe one decision tree will overfit to this training data. What we'll do is, let's say we have 1,000 training samples. We'll randomly select 500 of them, and we'll train one decision tree. That decision tree maybe has overfit to that subset of the data, that small subset of data. We'll then take another random subset of 500 points, train another decision tree. So that decision tree has seen a totally different data set, and it has built a tree that fits to that random subset of the data. And we'll keep doing this. Maybe we'll build 100 different trees on 100 different random subsets of the same data. Each tree may have fit to that subset, but on the overall, each tree, when has seen different samples of data, when you want to predict, you ask each tree, what do you think is the pixels value? Each tree will say, based on my training, this is water. Second one will say, based on my training, this is not water, and so on. Out of 100 trees, maybe 70 of them will say this is water. 30 will say not water. We'll say, okay, majority wins. Most of the trees, even though they're trained on random subset data, they all agree that it's water, so we'll mark it as water. And what we found is it's like a wisdom of crowds. when each person has a different worldview. We all have different experiences, but if you ask enough people, ultimately they'll converge on the right answer. So if you train different models on different random subsets, they'll converge on the right answer. And this works surprisingly well. The random forest has been proven to have very high accuracy compared to single decision trees. This kind of learning is called ensemble learning. That means instead of just having one model, you use a set of models and you use all of them for your prediction work. So random forest is an ensemble learning algorithm that uses multiple decision trees. This is a diagram that shows how it works. You build multiple trees from the random subset of data, and then you ask each tree. In this case, it's asking the tree 1 says class A, tree 2 says class B, tree N says class B, and so on. And you take the majority voting, and then you decide the final class. And remember, this is happening at each pixel. At each pixel, you have hundreds of trees that are trained, and at each pixel, when you want to predict, you'll go and ask all the trees, you'll take the majority value, and then you decide on that. It has been shown in remote sensing that random forest outperforms all machine learning algorithms for most cases. There have been many studies that compare different algorithms with different kind of modeling systems, and the kind of TLDR of all of the research is that random forest is a great starting choice for your modeling purpose, because it outperforms almost all other algorithms, and it gives you good accuracy out of the box. So if you don't know anything else about machine learning and you want to implement something in Earth Engine, just start with random forest. You'll get good accuracy, and if you want to change or try a different model, it's a one-line change. You can just switch your classifier to a different one, and then you can see how the model performs. In the last few slides of this presentation, I have some references which compare different algorithms for remote sensing data set. And again, all of them say that random forest outperforms SVM and other algorithms. So it's a good first choice for when you're doing machine learning in Earth Engine. And once you have your initial results, you can always switch and try different models to work with it. The name random forest, random is because you are randomly subsampling your data into different subgroups, and forest is just because it's using different decision trees, using multiple decision trees in the algorithm, and that's where the word forest comes from. It has nothing to do with the physical forest that we think of when we think of satellite images. We will learn about neural networks in our module 6, where we implement a deep learning network using TensorFlow and work with Earth Engine. But so far, the idea is, hope you understand how these algorithms work internally. And the key thing to understand is all these models start with data, a labeled data. They'll try to learn from the data, build a model of the data that can be generalized and used to predict unknown data. And that's what we'll do. We'll build a model that will take our input image, we'll train a classifier. In this case, we'll start with a random forest classifier, classify the image, we'll do the accuracy assessment, we'll tune parameters, we'll process our input data, and then we'll post-process the data. So let's go and implement all of this workflow in Earth Engine. Let's switch back to the code. We got an introduction to machine learning and how supervised classification works in Earth Engine. We'll now go and implement the full classification workflow in Earth Engine. Just to recap, this is the workflow that we're implementing. We'll take our input image, we'll collect training data. In our case, we want to take our input image, classify this into 4 different classes. We want to classify the pixel if it's either urban, bare, water, or vegetation. So we'll take our image and we have to say, I want to detect whether each pixel is either of these 4 classes. So we need to label points for all of those 4 classes. We'll do this just by looking at the image and dropping points. Once we have this, we'll train a classifier, we'll classify the image, and we'll see the classified image. Let's go and implement this in code. We'll start our module 3 here, script 1A. Here we are working with the images for the city of Bangalore. We have the polygon for the city, and we have the satellite image from Sentinel-2. We just created a multi-band image, and now we have this composite image, a yearly composite, and we want to classify this. Yearly composite is useful because it's cloud-free, so we don't have any pixels which are cloudy, they won't get misclassified. And now I want to classify this into 4 classes. Let's see how we can implement this. The goal for this module is that all of you will have to do the same thing for your own chosen city. So once we learn how to do this, we'll have to go and collect the data for your own city and run the model so that you can classify your own city. At the end of this module, all of you will have a classification for your own city classified into these 4 classes. So first, let's learn the process. Right now, when I'm covering the A script, just look at my screen, understand the process, and then in the C script, when we do the exercise, you'll collect the data for your own city and do the classification. So first step, we want to collect the training data. We have 4 classes, so I want my classes to be urban, bare, water, and vegetation. So I want to collect some training samples so I can train my model into each of those 4 classes. When you're collecting training data and you want to label them as text, but computers don't really work well with text. So we'll use some numeric value to assign the label to each pixel. So we'll say all the urban pixels will label it with 0, bare will be class 1, water will be class 2, and vegetation will be class 3. This is just a scheme that we came up with. You can use any integers, different classes. All of these classes are such that we can see them from our satellite image. Sentinel-2 is pretty high resolution, so you can differentiate between different classes. If you're working with lower resolution data, you may have to go to the field and collect the data. You just need the coordinate of that particular place and the label for that. In this case, let's start collecting data for urban. And you can see in the city, urban regions are pretty easy to find. You can see the built up regions. In this case, we are defining urban as buildings plus roads and any impervious surface. So you can think of any of the surfaces which are built up, we'll classify them as urban. Here, Earth Engine gives you some drawing tools. We're going to drop points. So this is a marker tool. I'm going to click this marker and I want to drop a point where there is urban region. I want to zoom in till I see the pixels. These pixels also are quite big. So it is possible that if you zoomed out and drop a pixel, if I want to drop my pixel here, I might accidentally drop it on this pixel, which looks a little green, which might be a tree. So make sure when you're dropping your point, you are dropping it on exactly an urban pixel. So I say, okay, this one is an urban pixel and I can drop a point. If I'm not sure if what is at this urban pixel, I can take help of the high resolution base map that Google provides. I can switch to the satellite view here and turn off my top layer and say, what am I looking at? And here you can say, this actually looks like buildings. Remember to use the base map only as a reference. This base map imagery may be from a different date altogether. We are trying to classify images of 2019. This photo might be 2024. It might be 2004. We don't know. So your satellite central imagery might say, oh, there's a building here, but that building might have been demolished in the satellite image. So again, use this as a reference just to kind of get an idea of your landscape. But when you're dropping the pixel, always use your sentinel imagery as a reference. So let's say if this is one training sample that we want to use as our training data, we want to store both the points as well as this attribute value, that it's a 0. We want to store the label along with that. So by default, when you put something on the map, it's stored as a geometry, point lines, polygons. We want to change it to a feature collection because feature collection is like shapefile. It can hold both geometry as well as attributes. So we'll change it to feature collection. We'll rename this to be urban and we'll add a property. We'll use a property called land cover to designate the class of that pixel. You can use any name. The way we have written the script, we expect this property to be called land cover. So for your exercise, use land cover, but it could be anything. It could be any property that you want. And we'll say the value is 0. So all the points I drop into this collection called urban will be value 0. And I can go and find some other urban pixel. I can say I'll drop a point here. You can see I'm dropping points into this collection. You should take examples of different types of surfaces. So make sure you take enough samples on the road. So this is a street. You can see this is a pixel representing a street. That's also an urban surface. So we'll drop some point there. We'll also look at different parts of the city. We'll not concentrate on just a single place because maybe one part of the city has a different material and you're not training your model on all possible examples. So make sure we distribute points evenly. Even let's say a runway is an impervious surface. We want to classify them as urban. We're going to drop point here. This is a building roof, which also we want to classify as urban. So show different examples. So your model learns from all the examples and say, for all of those cases, I want to learn that this is urban area. There's a question on how many points are enough. This is quite a small area. So it's just a small city and we have just 4 classes. So in this example, even 10 points is good enough. So if you just take 10 points, good enough. But as I mentioned earlier, my thumb rule is around 100 points per class for a regional classification. So let's say you're working with a large county or you want to classify an entire state, 100 points per class is a good starting point. For this simple classification, even 10 points will give you pretty good results. Many times people ask me, I want to use machine learning. I said, machine learning, the acronym ML is well suited because in ML, most of the time is doing manual labor, ML for manual labor. So that's why you'll be collecting and cleaning data when you do machine learning, and that's where most of the time goes. The modeling, there's a script, you just run it, and the computer will do the rest of the work. But yeah, data collection and cleaning is a big part of your machine learning process. So Earth Engine also allows you to draw polygons. So for example, let's draw a polygon like this, and Earth Engine will create one training sample per each pixel, and that'll give. So suddenly you've got like 1,000 training samples. Can you do that? I strongly recommend doing against it. Do not do this, because when you do this, Earth Engine is going to take each of the pixels as your training sample. Are you 100% sure that every pixel in this polygon is just urban? There is not a single pixel of vegetation or bare or other classes. If there are, they will also be labeled as urban, and you'll get wrong results in your output. In machine learning, training data is gold. Most algorithms will treat your data as complete truth. And if you have wrongly labeled points like these, it'll mess up your model. So I recommend collecting points with a lot of care and make sure you're dropping points in the right place, or you're going to the field and collecting. And having a good, accurate training samples will save you a lot of work later on. All right, so let's say we have collected all the data for urban points. We want to now move to the next class, which is bare class. So I would come here, click new layer. Again, default type will be geometry. I'll go to settings, turn this into a feature collection, maybe keep bare. Property will say land cover, and we have said that land cover of 1 will be bare. You can also change the colors if you want. And now we have this new collection, which is bare, and we can go and drop points on any bare surfaces. In this case, we are defining bare as any pixel which is bare ground. There's nothing constructed, it's just bare soil. So we can go and drop points. So I can select the bare place, and then just drop points on this. So it's this, and drop points. So this one is bare, and so on. If the city that you're trying to classify or the region trying to classify doesn't have any bare soil, it is okay to skip this. There are many instances. For example, if somebody was trying to classify Tokyo, you'd be hard pressed to find any bare soil in Tokyo. So again, you can skip that if your region doesn't have any bare soil. Make sure you collect data in different parts of the city, which has the same class, and you can drop points here. So when you're dropping points for one class and you say, I found a good example of this other class, you can switch layers. I can say, I want to now drop a point for the urban layer. I can drop points for the urban pixel and so on. Similarly, I will add another layer for water and another one for vegetation. And once I've done, I'll have something like this. I'm going to show you the final training samples. You can see I've collected few training samples for each of those. This is what my training samples look like currently. I have a few points for urban, some for bare, some for water, and some for vegetation. They're well distributed throughout the region I'm trying to classify. Around 10 points per class is good enough for the small region. If you are working on a larger region, add more points, but this will give you a pretty decent result for this. So now we have those classes. We have labeled each class. This one is 0, the second one is 1, third one is 2, and this one is 3. Right? So we have these 4 unique values, and the goal is now we want to use these training samples for our classification. We have 4 different feature collections. It just makes it easy to merge all of them into a single training collection so that we can use them together. So the first step is we'll merge all the training samples. I'll define a variable. We'll use the variable GCP. GCP stands for ground control points. It comes from the fact that remote sensing people used to collect data from the ground. Even though we're not ground to the ground, this is what the workflow looks like for remote sensing, that you have your GCPs. We have this urban collection. We'll use the merge function to merge it with the bare collection, merge it with the water, and merge it with the vegetation. So now I have a single collection, feature collection, which is got all my training samples. At this point, it's just feature collection where you have only one property, land cover. There's only one column in my shapefile, which is land cover. the value is different based on whether this pixel was labeled as water, vegetation, bare, or urban. Next step is we want to now have, for our training model, we need to have this table. Remember, we need this table. The classifier expects the label along with the reflectances. We only have the labels. We don't have the reflectances at each of those pixels. We have our image. If I look at my composite image, we have an image containing 12 bands. At each training sample, I want to know what is the reflectance of those bands at that pixel, so I can take this and train my model. So next step is to extract the pixel values. For doing this, we're going to use this function called sample regions. We'll take our composite image and run this function called sample regions, which is a function that allows to extract pixel values from the input image at the given points. So it says, what is a collection containing the geometries? We'll say this is the GCPs. Properties, when you have your feature collection, sometimes, if you uploaded a shapefile or you have some other information, which one do you want to keep in your training data? Whatever you specify will be kept, other will be removed. So we just want to keep this one land cover property. So we'll just say keep the land cover, you can remove everything else. At what scale you want to sample, we are working Sentinel-2, so we'll do a 10 meter. The rest of the parameters are optional, and we can run this. Let's see what happens when we run this function. So remember, we had this training samples which we had labeled. Once we run the sample regions function, each of those will now have extracted the spectral values from each of those bands from the composite image. And now we have 13 properties, band 1 through band 12 of what were the pixel values and the land cover to predict. So now we have a table which says I have these columns which are to be used by the model as an input. If I give you this set of numbers, you have to predict the output to be 0. If I give you this set of numbers, you have to predict land cover 2, and so on. So this becomes our table. Okay, so we have done our table, and now we can train a classifier using this train data. So let's train a classifier. What classifier you want to use? Let's look at the docs tab. All the classifiers that are available in Earth Engine are under the e.classifier module. These are the different algorithms that are available. If you want to train a SVM model, you can use this classifier, libsvm, support vector machine, and it can train a SVM model. If you want to train a decision tree, you can use this. There are other algorithms like KNN and name-based. We want to use random forest, so we'll use this classifier, which will create a random forest classifier. So we'll say e classifier small random forest. So this is the classifier, and we want to fill different parameters. You can see the classifier has so many parameters. The only one required is the number of trees. How many trees, decision trees you want to use in a random forest. All of these parameters will discover the optimal value later on. Right now, we'll just put something. It doesn't really matter what you put in. So let's say I want to put 50. I want to use 50 trees. Well, why 50? Well, I just feel like it. There's no reason behind it. Once we have the model, it's working, we'll optimize and say, I have this model, optimize it, and discover what is the right set of trees for this model. Okay, so we'll do this thing called hyperparameter tuning. So for now, we'll start with 50. Okay, we have a classifier. We want to train it. All classifiers have this train function. So we'll say, I want to train it. What are the features for training? Well, we have our training features. Each of the training features has some properties which are used as input and one as output. So what is the class property? Which one you want to predict? You want to predict the stuff contained in land cover. What is the input properties? Well, it's all the properties like band 1, band 2, and all the way till band 12. Right? These are the input properties that we want to use. Since this was anyway sampled from our class of composite image, we can just say the name of the properties are the same as the band names of the composite image. So you can just use the shorthand saying whatever the image it was sampled from, you can just say composite.band names. This function just gives you the list of bands that were there in that image. So you can use that as instead of just manually defining that. and done. So we have trained our random forest model. We initialize it with 50 trees, train it with our training data, and now we can just say our model is trained, let it predict all the unlabeled pixels. So it says, I have so many pixels, thousands of pixels here, go through each pixel. You'll know the 12 reflectance values at this for different bands. There'll be the input, try to predict what is the class and show me the result. So let's classify the image. We'll take our composite image and run this function for classify, and we'll give it the train classifier. And we are done. Let's display the image. We need some viz params. What should be the viz params here? 0 to 3, because my classified image has only 4 pixel values, 0, 1, 2, and 3. So I have each pixel will be turned into one of those classes, which will be either 0, 1, 2, or 3. So my min is 0, max is 3. And since it's a one band image, it's just one band of classified image, I can give a palette which will display this in different colors. You can use any palette that you want. I'm just going to use this 4 colors that we have used here. So whatever color you specify here, this will be class 0, class 1, class 2, and class 3. Let's add it to the map. We'll say add it to the map, classified image, slash parameter, and super classified. Now when I run this, Earth Engine is now going to go backwards and say, I need this classified image, I need to train this image, train this model, and so on. It's going to run. You can see it's training the model. It's now predicting each value of each class and streaming the result. I just want to clip the data to the geometry that we have trained a model for, and we'll see the result of our model. So once we run it, Earth Engine will predict each pixel, ask each model, what is the value of this class at each pixel, and you're going to see the result. And you can see our final classified image. And as I zoom in, you will see Earth Engine will just perform classification in real time and predict the value of each class here. You can see that even with just a few training sets that we collected in just a few minutes, this is a pretty good model. It is able to classify the image quite well. You can see, compare it with the input image, and you can see it got detected all the bare, urban, water, and vegetation pixels quite well. And this is the kind of power of machine learning and cloud computing, that just with few training samples, we're able to train a model that can go and classify every pixel in the image in real time. The unique thing about here is that you are now leveraging a lot of parallel computing in the cloud. You don't have to download data. You don't have to wait for all the computation to finish. You can now do this in real time. But algorithms that I use are the same as used anywhere else. Even the random forest classifier that is based on an open source library called Smile. So if you want to know what is the implementation of random forest algorithm, there's this Java library called Smile, which has implemented all the machine learning algorithms. And since Earth Engine backend is written in Java, when you run this function, it uses this library to build a random forest model and use it for prediction. So again, it's all based on open source models and open source workflows. What you get in Earth Engine is be able to ability to do this in real time and at scale. You can now do a country scale classification in real time versus it takes months to do this on the desktop. We are ready to do our exercise. So in our module 3, we're now going to work on our exercise. Vigna, you can explain the exercise.
Yeah, so for the exercise 1C, we want to perform supervised classification for the city. So here, the first step would be to replace this geometry. So you can just delete this one and create one new geometry at your chosen location. So let me show you my hometown. And here you see that I have hometown Jamnagar, and I can just create one polygon here. And I would like to perform classification for this region. So this is my geometry. You see that this is the geometry which is added here. I can just see that we have this script where we are creating the composite and we are adding that composite to the map. So this is the clipped composite for this geometry. So let's just run the script and see the composite. Yeah, so here you can see your composite. As soon as you get your composite, you can start taking training samples for all these 4 classes. So you see that we want to assign values like 0, 1, 2, 3 to urban, bare, water and vegetation. So start by taking points for urban. So let's take points. So, okay. Let's say one new layer. You can change name to urban. We want feature collection. So here it is feature collection. We will say property land cover and give it a value 0 for urban. You can give some color to this points so that you can identify that you are using this color for particular type. So you can take something like red for urban. Say okay, and just start by taking points for urban. So let's zoom in. You can keep the satellite image in the background for the ease, but always wait for your original image to come up before taking the point. So I see that these areas looks like urban. So I'll just wait for my image to load. This is the image and I'll just take a picture over here. So these are my urban points. Let's go to some roads and take points there. So always try to include roads as it is again an urban infrastructure. So not only buildings, but take points on the roads here. You see, these are some roads where I want to take points. So likewise, you can just take points for urban. Just find, you can take around 10 points for each class. Start with urban. Let's just do one more. Same way, you can just add a new layer here, geometry. Convert it to feature collection. This is where we are giving it a property named land cover. So this
property. Remember, the property name has to be small case, exactly spent as land cover, because that's how what we are assuming in the rest of the code.
So this can be anything, but for the script that we are going to use, we are going to spell it exactly like this. So just keep it the same way so it works for you for the exercise here. So do this and take some points at better land here. So I can see some land which is barren. Also, you can just switch between layers while taking picture. So this is the urban class. I'm taking picture for urban class. If you feel while looking for this urban class, you feel like taking picture for another layer, you can just switch. I can switch layer and just take point for urban in between. Again, I can switch and take a point for bare class. Likewise, you can just do this. You can also move points. So you have this pen symbol here. You can move these points. Just click here and drag to move the point. You see that we also have the option to delete. So when you use the pen, you have this option to delete as well. So do it like this. I'll show it once again. So when you have pen, you can click on here, you can move. Also, you can delete. So likewise, you can get around 10 points for each class. And then we will just uncomment this portion of our script. So you see that this portion does the GCP part. We are merging all the feature collections to get the GCP. We are training the classifier, and then eventually we are doing the classification for the image that we have clipped for our region. So just do this. Try to get all the feature collections and then comment the portion of script and run the script so that you will get your classified output here. And
I'm going to share some tips on the screen to help you perform this data collection exercise better. Make sure you are always dropping points on Sentinel-2 imagery. That's your reference. If you try to use the high-res imagery, it may not be from the same time. So do not rely on that. When you are selecting a pixel for a training sample, make sure you're dropping it on the Sentinel-2 imagery. Distributor points across the city. Make sure you take points on streets. The most common errors we see when people do this for the first time is you will have water and dark streets getting confused. So make sure you have water if you have points on the streets. Also, if you have water which is covered with vegetation, do not take those points. Try to take examples of pure pixels and let the model figure out how to classify mixed pixels. So show examples of pure water, pure badland, and so on. Do not take input data as your training samples on the mixed pixels. Control// is for the bulk comment. So make sure you use that shortcut to uncomment all the lines together. So try this out and see if you can perform the supervised classification for your city. We'll move on and learn how to assess the accuracy of a classification. Let's say you've done your classification. Some of you are happy with your classification of the city. Some of you are not too happy. If you're happy, how happy should you be? Is it perfect? How good is it? Is it 100% accurate? Is it 90% accurate? What if you want to improve? You said, I want to spend more time. What if I collected 100 more training samples? Did it improve or did it not help? How do I assess that? It'd be helpful to get a numeric measure of the accuracy so that you can compare it against the previous version and say, okay, I did something, it helped improve my accuracy. So let's learn the concepts around accuracy assessment. Accuracy assessment is a formal technique to assign a quantitative number to your classification that will tell you how good your classification is. The common way that is done in machine learning practice is you have your training samples. Let's say you have 100 samples. Instead of using all 100 samples for training your model, you say, I will use only half of them. 50% of my samples, I will not use for training. I will only use the 50% of my samples for training my model. Once my model is trained, I'll ask the model, can you predict what is the class at the other 50 points? And I'll check the model's answer against the ground truth. And if the model got everything right, that means the model is doing well. So typically you take your training data and divide into two fractions, training and validation fraction. Depending on the setup, people use 70-30 split or 60-40 split, 70% for training, 30% for testing, and so on. You only train your model using the training fraction. The model never sees the validation data when it's training. So once you train and say, I'm done with training, how good is the model? You check the model's answer against the validation fraction. And in validation fraction, it's also this points that you have labeled. So you know what is the ground truth. If you label the point as water and the model said, I predicted this to be vegetation, then you say, okay, the model got it wrong. The model got it right. You say, okay, model got this right. So it performs well for predicting this class. Once you do this for all the samples that you reserve for validation, you can generate something called a confusion matrix between the actual value that you labeled and the model's predicted value, and you can compute some numbers for assessing the accuracy. The metrics that people use, one is the overall accuracy. How out of all the samples that I had reserved, how many of them the model got right? And this is one number that is very useful. You'll use this a lot to tweak your model for tuning your parameters and so on. There are other numbers in machine learning that you call it precision and recall. In remote sensing, you call them consumer's accuracy and producer's accuracy. These are different ways to looking at the same data on how good is your prediction versus how good it is at finding all the instances of the particular class. So a model can have high accuracy, but it'll miss a lot of the classes of that particular pixels of the class, or it can find all the pixels, but also make a lot of mistakes. So you want both good accuracy and good recall for your model. And those metrics will tell you what those are. Typically, these are not used too often in practice. But again, when you're writing a paper or you want to write a report, you can compute those and you will have those numbers. There's also kappa coefficient. Again, is a statistical measure of how good your assessment is, how good your classification is against a random assignment. And finally, something called F1 score. In remote sensing, most people use overall accuracy as the main metric for tuning parameters and improving the model. In machine learning, you use an F score, which is the average of both precision and recall. And F1 score is something that you want and say, I want to do things that will improve my F1 score. Whether you use F1 score or overall accuracy, it really depends on whether you're coming from a machine learning background or a remote sensing background. It's the same concept, just a different metric that you use. Earth Engine allows you to compute all of this, and you can use any of this that you like for your assessment. You can compute all of this in Earth Engine. Once you have your validation data and you do your accuracy assessment, you'll get a matrix like this. This is called a confusion matrix. Here, it shows the ground truth values as rows. So you can see these are the classes that you had labeled. On the columns are the predictions. These are the model's predictions. If you see stuff around the diagonals, here it says there are 43 samples which you labeled as 0, and the model said they are also 0. So model got this 43 right. This 3, you labeled 0, but the model thought they were 1. So this is where the confusion is. So that's why this thing is called confusion matrix. Anything that is not in the diagonals is where the model got confused. So if you generate this confusion matrix and everything is in the diagonals, you're all good. If you want to improve the model, you said, I want to reduce the confusion and I want to focus on this class. There's some confusion between class 0 and class 1. There's some confusion between class 3 and class 2, and so on. If you want to compute the overall accuracy, it says all the numbers in the diagonals versus the total samples. That's my overall accuracy. How many samples were right divided by the number of total samples. So in this case, we have a 93% accuracy of our model. Similarly, you can do for each class that there were 46 points of class 0, only 43 were detected correctly. So this is your producer's accuracy. So 93% is the producer's accuracy for class 0, and so on. You'll get one number for each class. Similarly, if you do it for column, you say there were totally 48 class 0 samples. My model found only 0. It missed 5. And this is called the consumer's accuracy. And this gives you a kind of different view of the same data and say, this matrix will show you different slices of the same data. Again, as I mentioned, in practice, what you do is you see your confusion matrix. You want the stuff outside the diagonals to be low. If, for example, in this case, if there were 30 here, I say, okay, there's a lot of confusion between 0 and 1. I'll go back and add some more training samples for 0. I'll review my training samples for class 0 and class 1 to reduce the confusion. And once you are happy and generally you have a decent accuracy, you'll say, let me go and optimize this number. So you just start tweaking and doing your tuning so that you have a higher overall accuracy. Okay, let's implement the accuracy assessment in our script. We'll start working on script 2A. At this point, I have this GCP variable where I have some GCP points and I have done the classification, and I'm just running the same workflow that we ran in the previous script. We have whatever GCP we had collected as individual layers, urban, bare, vegetation, and water. We have merged it and we have a single GCP layer which we want to use. Now let's run this. When you run this, it goes through the workflow and we have the classification, which is now this looks pretty good to my human eye, and it assesses and it says pretty good. But again, we want to know how good is it? Can we assign a number to it? So then when we add some additional parameters and tweaked parameters, we want to know whether it improves or not. Let's look at our GCPs that we used. So here I'm going to print the GCPs to print dot size. So in this case, we have 447 GCPs. So it's a larger region. This is one of the hydrological basin around the city of Bangalore. We have collected 447 training samples, and we used all of them in our training. Let's not do that. We have enough training samples. So what we can do is we want to do accuracy assessment. So we'll divide the training samples into two fractions, a training fraction and a validation fraction. We can do 60-40 split. So let's do 60% of the data which will go to training, and 40% will go as validation. So we have this number of points and I want to divide them into two fractions. Now, how do I divide it? I can't do it manually. If I do manually, I'll include my bias. I can't even do it in the sense like, let's take the first 60% as training and the last 40% as validation, because all the first 60% might be for a single class. So I want to do this in a way that doesn't include any bias. And the right way to do this is we want to randomly split the data. So we don't have any bias. Now, how do we do the random bias, random split? Let's print the GCP thing to see what the GCPs look like. So we have this GCP variable containing all the training samples, and you can see we have this each samples. We have this just land cover property, and this is the values from 0, 1, 2, 3, and so on. Right? So we have this properties. Earth Engine has this function that if we take the GCP and run this function called random column. If I run this, it's going to run this function and assign a random value to each feature. You can see we just had land cover, and now each feature has this land cover along with some random number. This random number will be between a random number between 0 and 1. So when we run this function will assign a random value between 0 and 1. Each feature will get some random value. Let's look at the documentation for this. this says by default, this function creates a random distribution which is uniform. That means there's equally likely to have any number between 0 and 1. So I have some number. Each number is equally likely to between 0 and 1. You can also make it a normal distribution if you want to have a normal distribution. But for this purpose, uniform distribution is important. Now, you have all the points. I've assigned some random number to each of the features. And since there is a uniform distribution, I can say I want all numbers where the GCP, where the random value is less than 0.6 to be saved as training data. So everywhere this random baseline value is less than 0.6, they'll go into training fraction. So this will give us randomly chosen points, which are roughly 60%. Why roughly 60%? Because it's equally likely to have all values from 0 to 1. And when you say 0.6, you're going to get approximately 60% of the points saved as training samples. The remaining can go into validation. So I will say for our validation GCP, we'll apply a similar filter. And this time we'll say greater than or equal to 0.6. So 0.6 and below will go to training, 0.6 and above will go to validation. So this will have roughly 40% of the points. This will have roughly 60% of the points. We are using a different predicate here. This is less than and this is greater than. So less than 0.6, 60% will go to training, rest will go to validation. And we can also print the validation GCP.size. Sorry. So we had to do this. We created a random column, but we didn't save it. So we'll just save it into the same variable. So when we run the random column, we'll assign this random property, and now we can use this. And you can see the split worked. We had 447 points. We have chosen 271 points at random that go to training. 176 will be reserved for validation that will check our results against. So once we run the split, when I do training, I don't use GCP. I use only training GCP. And I run my model. So I train my model. I train a classifier, so I extract all the values from my composite at the training GCPs, train my model using only the training fraction, and then classify image. And when this image loads, you'll see that this is the classified image that was trained only using this 271 points. We have not used 176 points. Those are the points where we know the answer because we have labeled them. So we can now go and check how did the model predict those points, and we can generate our confusion matrix. One of the things that I can do, there was a question earlier around the tile scale parameter. When you have functions like sample regions, they have this additional parameter called tile scale. When you are working on large regions and you have a lot of data, sometimes setting the tile scale higher will speed up your process. In this case, I can set the tile scale to a higher number, and it can also speed up my classification. So when there's functions that take tile scale values, if you get an error that the tile values are too large or the tiles are very large, you can set your tile scale parameter. The tile scale parameter will divide your region into smaller tiles, and each tiles will be processed by more machines. So that'll help you speed up the workflow. So now I have my classified image, and I want to test the result of my validation fraction. So let's do my accuracy assessment. Again, the approach here differs from the remote sensing practice and machine learning practice. In remote sensing practice, what do you do once you have your classifier? Well, you'll go and classify the image. And when you classify the image, the model has actually predicted the value at each pixel. You have the result for your model's prediction at every pixel already available to you. So now I have some validation data. So let's say I have my validation points. Let me print that. I have my validation GCPs. I'll print my classified image. So I've gone and classified every pixel of this image. The model has predicted what the class is at every pixel. So I have this classified image with the classification band, which knows the model's prediction at every pixel. I have those 176 points where I only know my label. I only know my land cover label. I don't know what is the model's prediction. How do I check my answer, my label against the modeled answer? Well, I can simply check what was the value of the classified image at that pixel, because the model has already classified it. Each pixel has already been predicted. And I can just say, let me go and sample this image classified, and I'll know what is the value of the class at that pixel. So let's go and try to do this. So I will say I'll take my classified image, which has got models prediction at each pixel, and I'll just sample that. We'll say I have my validation GCP as the input. I want to only keep the classification property. Oh, sorry, I'll only want to keep the land cover property. We'll sample at 10 meter. Let's see what this test feature collection contains. So I had the value of the model's prediction, and I had the GCP with the labels. And when I sample that, I'll have my 176 labels, which I had labeled with land cover data, and I'll extract the model's prediction with the values that are the classified image. And that becomes my input to generate the confusion matrix. In machine learning practice, you don't have a classified image. So in machine learning practice, people will actually say, I have my model, I'll go and classify this validation GCP, and then I'll check the results against that. So it's a slight different approach for machine learning. In remote sensing, you first classify the image, so you can just directly sample the classified image. And if I look at my output, now I have two properties. Land cover is what I had labeled. Classification is the sample from the classified image, which is the model's prediction. And I have those two values at every feature, and now I can generate a confusion matrix. So let's just generate our confusion matrix. There is a function called error matrix. Which takes the two properties and generates the confusion between those two. So we say, give me the confusion between land cover property and classification. These are the two properties I have available in my feature collection, and you can print that. And you can see this is my confusion matrix. And you know already how to read it. All the stuff in the diagonal is the one that model got correct. The stuff that is not in diagonal is the one that model got mistaken. When you run this error matrix, the output type of object you get is this object called e.confusionMatrix, and you can compute different numbers. So if I want to compute different numbers, I can just say print test confusion matrix.accuracy. And this will tell me what is the overall accuracy of that confusion matrix. And you can see it's 93%. So that is the accuracy of my classification. And now I have a single number that represents how good my classification is. I can now go and test different parameters. What if I train a model with 100 trees? What will happen? Will my accuracy improve or reduce? I can now check it. And then I can have a script written to optimize for the overall accuracy. And I can say, what if I add new bands? What if I add NDVI? Does the model improve or not? So having a number that gives you how good your classification is quite helpful, so that you can judge and improve your model and so on. So Vikna, you can explain the next exercise.
Yeah, so for the exercise here, we have the training GCPs, validation GCPs, we have the classified image here, and here we are testing the accuracy by creating the confusion matrix, and we have overall accuracy as well. We want to assess some more metrics here using your confusion matrix output. So this is your confusion matrix. Test confusion matrix is your output. Using this as input, you can calculate producer's accuracy, consumer's accuracy, and F1 score. So we have functions to calculate this directly in Google Earth Engine. So search under this module and you will find functions to calculate this. You can just calculate and then print all the elements, all the metrics that you have calculated using confusion matrix. So you see you have this consumer's accuracy, F score, and producer's accuracy. Use these functions, calculate and print it.
Our topic of accuracy assessment, I'm going to cover some new material. Let's learn about this technique called K-fold cross-validation. We learned about accuracy assessment in machine learning. The typical way it's done is you split your training samples into training set and validation test. You train the model using the training set, test it using the validation set. This is also called holdout method, where you say, I'll hold out the validation fraction and I'll build a model using the training fraction and I'll test it. Now, this is fine, but you are testing a model against only one time, one instance. What if you randomly split your data and the random split you got is much favorable to the model and model just performed really well? What if it was just luck that you got a really nice data that the model can predict well? Right? It could happen because it's a random split. So what people want to do is like, can I trust this number? I got a 95% accuracy. Is it really because I got a really favorable split of my training test data, or is it really 95%? So what you can do is you can say, I'll repeat this process with multiple times with different kind of training and validation set for my data. So instead of just doing one time split of 60-40 or 70-30, I'll do this multiple times. And when I test it multiple times, I'll know whether the model is really good at training using whatever different data subset and predicting using different subset. And this method is called k-fold validation because you divide your training set into k folds and then take one of those folds for validation. The remaining folds are used for training, and you do this k times. So typically the number k people use is 10 times. So you repeat this process 10 times with 10 different subsets as validation and training. Let's see this visually. Here, let's say you have all the samples. Let's say you have 1,000 samples. The first step is you randomly split into k subsets. So let's say we are using 10. So we split your training sample into 10 subsets. 1,000 points were there. We split into 10 subsets of 100 points each. In the first iteration, you say the first 100 points that I got, I'll reserve for validation. I'll train my model using the 900 points. I'll train a model using those 900 points, test the accuracy on this 100 points, which I'll hold for validation. And I'll get some accuracy number. If you want to know, was this really luck or was it really, model is really good? Well, next time, in the next iteration, we take those 1,000 points, take the second fold as validation, use the remaining points for training the model again, and test it using the second fold. And we'll get some different accuracy because the model has now seen different data and it was tested on the different data. And you keep doing this. So you do, if it's a 10-fold validation, you just keep doing this 10 times and you'll get 10 accuracies, right? Each time the model is trained using a different training data and was tested on a different subset. And your final accuracy is the average of all accuracies. And this number will be more reliable because you did 10 times the same thing using different subsets. So just doing it once. So the algorithm for k-folds cross-validation is we randomly split our data into k-folds, train the model using k-1. So if it's 10 folds, use 9 folds for training, 1 fold for validation. Compute the accuracy metrics, either you do overall accuracy or F-score, whatever accuracy metrics you want to use. Compute that, repeat the process for all folds. So repeat the process 10 times, and then average the accuracy metric for all runs. And that's your final number. And this is more robust method for computing accuracy. We have the code available for this in the supplement. Let's go through the script and learn how the code works. So in your end-to-end G repository, we have the supplement folder. There are a lot of useful scripts here. This script is under supervised classification, k-fold cross-validation script. We're going to use the same GCP that we are using for our module 3. So again, around 400 points are there. And we want to repeat a process 10 times. And again, when you think about how you want to implement such functions, such things in Earth Engine, you think about how can I do it one time, and then I'll map the function on something that can do it 10 times. So we say, given, first we'll split our folds into 10. So this function just says, give me features, how many folds you want to split into, and it'll just run some filters and return training and validation set for all the 10 folds. It's just splitting the data into 10 different folds in this case. So once we have the folds, we say now I have my 10 folds. I want to run the accuracy assessment for each of them. I'll write a function. Say given one fold has training and validation. How do I do accuracy assessment? And that's simple that we have done so far. So given one fold, this code is the same that we have done earlier. Training, validation, sample the regions, train a classifier, and check the accuracy. And so this is our accuracy. And instead of printing it, we can just say return this as a feature. In Earth Engine, it's useful to write functions which return features or images so that they can be put into a feature collection or image collection. Those objects are much better at filtering and doing stuff with Earth Engine. So generally, instead of returning just a number, you can just return a feature. And we say, this is the accuracy for this fold. And now we say, I want to map this on all the list of folds that I have. And I get a list of accuracies. So let me just run this. So I get 10 numbers. I do 10 fold validation, I get 10 numbers as output. So you can see in the first fold, accuracy was 97%. It's great. I think they got a very favorable fold for this. The second one is 91%. So there is some variation. There's some randomness in our model, which is causing this to happen. But again, if you do it 10 times, and then we say, I want to average out. And again, how do you do average? Think about statistics. What do? I use a reducer. So we just say, I have my list feature collection. I can run this reduce column function with a mean reducer, and I get the mean number. So the mean number is 95%. So now instead of choosing by chance, choosing a fold which gives you 97% or 91%, now you have a more robust answer saying, okay, I tried this 10 times, the accuracy is 95%. I have good confidence that my model is actually doing good. All right, let's start with our next script here. We're starting with the script 3A in module on supervised classification. This is what we've done so far. If I run the script, we have made a Sentinel-2 composite for a year. We have some training samples. We've split them into two parts, training and validation. We've trained a model with the training GCPs, and we've predicted our classified image using the classifier that we trained. And then we assess the accuracy using the validation fraction. And we got, say, 93% accuracy. This is our confusion matrix. To assess this, we can do both visual assessment and say how good is the classification. We can compare it against the Sentinel-2 image. We can also look at the number. And if you are happy with it, that's great. But what if the classification is not good? What if it's getting confused between certain classes? What if you want to further improve it? I'm going to teach you some techniques that you can use in your scripts to improve your classification. At the bare minimum, all of you, when you're working on a classification project, you should do 3 of the things, at least these 3 things at the bare minimum. We'll teach you a lot many advanced techniques, but at the minimum, you should be doing these 3 things to improve your model accuracy. So let's see what those are. So we are at 93% accuracy. Let's see if we can make it better. I'm going to comment out this part for now, and we'll do this one step at a time. So let me print my composite. The first thing you should do is whenever you are selecting images and creating composite, this composite is still contaminated by clouds. There are still clouds in there. So if you're taking a median value, and if you're a very cloudy region, you still may have clouds. That's a problem. Even if you don't have clouds, the median value is not representative because clouds are no data. So we should at least apply a cloud mask. Let's get our cloud masking function. You can just get the Clouds Code Plus for Sentinel-2. This is the best available cloud mask that is available. Or for Landsat or Modis, just use any cloud masking function that is available. And we're going to now do the cloud masking, just copy paste whatever code is there. And now we have this filtered masked collection, and we just use that to create a median. So now we have this composite that is created, a 12-band composite that is a much better representation of the ground truth because it is not contaminated by clouds. And for many of you who are working in very cloudy regions, you'll see a drastic improvement. You might see a hazy composite before because you have a lot of clouds that were still there. Now with masking clouds and doing the composite, you'll get much better image. So that's the first step. Always do cloud masking. In all of your scripts, the workflow should be start with the collection, apply filters to select images you want, immediately do a cloud masking. Map function to do cloud masking, and then start doing work because you don't want to work with cloud contaminated pixels at all. So that's done. We have our composite. What are the other things we can do? Here we are building a model that gets the value of this 12 bands, and it has to predict what is the class. The classes that we are trying to predict are things like vegetation, water, urban, bare. And we have learned so far that there are remote sensing indices which are much better at figuring out what the surface type is. If you want to predict some pixels to be a vegetation or not, instead of giving all the raw bands, we can give the ratio of the NIR and red band. which is NDVI. And NDVI is much closer correlation to vegetation than any of the bands. So we can help the model learn better by saying, instead of just learning from the bands, can you also learn from the spectral indices? We'll give you some indices. You can learn from that, figure out if that helps you predict stuff better. So second step that we must do. So first is apply cloud mask. We've done that. Second step that we should do is add indices. Let's add some indices that will help our classifier predict things better. Here I'm going to bring in a function. This function computes 4 different spectral indices. NDVI will help with the vegetation classification, NDBI, built-up index for our urban class, NDWI for water class, and then we have a bare class that we want to predict. So there's a bare soil index, and we implemented this here. Typically, I like to do at least 1 index per class that we are trying to predict. And there are many, many indices. If you just say, I want to predict a certain class, go and search, and you'll find an index that is designed to enhance the pixels of that class. So we have this function. We have our composite image with 12 bands. We can just say, I'm going to run this function on this composite image. It'll get this, compute those indices, and you'll get an image with the original bands plus those 4 bands. So I'm going to just save it as the same variable. So I don't have to change any code. So I'll say, just run this function to add those indices on my composite. So I'll run this. And now you can see my image has 16 bands. I have 4 extra bands in my image. And now if you see, if I print my training samples, I'm not changing any code. I just added a function that will add 4 indices. And now when I sample my training samples and say, extract the values from this composite image, I'll get 16 values at each pixel. So at each feature, we know that these are the spectral values, and these are also the index values at that pixel, at that training sample. And you can see this one is of class 0, urban. You can see NDBI is high, all the other indices are low. Let's look at some other feature. This one, let's look at this one, class 1, bare. And you can see BSI is high, other indices are low. And the classifier will learn from this. It says, wherever I want to predict 1, I can just use BSI instead of other values directly. And it is more important for me to determine. And you don't have to tell explicitly that use this. When the data is correlated with a certain class, the machine learning algorithm will just figure it out and say, I'm going to use this instead of just the raw bands. And that's the beauty of machine learning. You don't have to know what parameters are important. Just say, I have some data. I'll give you all the parameters. Figure out what works best and how can you build a model to predict things better. And we just added those indices. Great. So now we have these 4 extra bands, and we have those indices. The third thing we want to do is we want to add data sets which may be helpful in our prediction. So add other data sets. Depending on what you're trying to predict, certain data sets may help the model learn better how to differentiate the classes. Let's say we figure out that when we are trying to predict these classes, maybe slope and elevation might be helpful. So maybe there's a correlation between elevation and urban region, or maybe slope and water. We don't know. It might be helpful. We just have a sense that it might be helpful. Maybe have the model learn from slope and elevation. In Earth Engine, when you want the model to learn from some other data set, just find the data set and add it to your composite. It's as simple as that. So we'll just go and say, I want to use some data set. So let's say Earth Engine has many elevation data sets. We'll use this ALOS data set, which is digital elevation model, global elevation model, 30-meter resolution, and which has got information about the elevation of each pixel. So we can take this and we'll say, I want to compute slope and elevation from this. So we have we say, give me this elevation. And then once you have elevation value, Earth Engine has a function to compute slope of each pixel. And we say, we want to learn from this. So we can say, okay, I have my composite. I'll take this and add both slope and elevation as bands. So now my composite has 2 additional bands. It has got 18 bands. They're all spectral bands plus spectral indices plus elevation and slope. And when I sample that image at those training samples, my training samples will now have values of slope and elevation at that point. So it says, at this training sample, the elevation is this, slope is this. See if there is a correlation that help you predict 0 better. And we just added it. And people who have done this on the desktop or in a different system, you'll say, wait, what about projections and pixel size and all of that? Why didn't we have to worry about that? Why can't it just work? In traditional remote sensing, when you want to merge 2 different data sets, you have to match their projection, you have to match their pixel sizes, match their pixel grids, and then only you can sample from that. And that's a big pain point. And Earth Engine kind of designed the system so that users don't have to worry about it. Say, I have this different images in my composite. Each image has a different projection. You can see this one is in UTM, this one is in 6, doesn't matter. When we sample this image, we are saying sample at scale 10. So it's going to resample everything at 10 meter resolution. It says, you didn't specify CRS, I'm going to resample everything to the first band CRS of your image. So we'll reproject and resample everything at that resolution, at that CRS, and you can sample that. And this reduces so much friction in the ability to use this data. If you're doing this project and you want to do this using any of the software, you'll say, okay, now I'm going to go to Atlas website, download the data, mosaic it, reproject it, resample it, and then I can start using for machine learning. Here, 2 lines of code, and just add it to your composite into this. And you can now do the same thing. You say, maybe there's a correlation between temperature and my output class. Go and add a temperature data. You have a humidity data. Maybe there's a correlation between those. Go and add those images as bands, and your machine learning model starts learning from that. One more thing that you must do when you work with your classification, look at our training features. What we're doing right now is called feature engineering, where we're deciding what features we'll use for our model, that model will learn from. And one of the core principles in feature engineering is that the absolute value of each feature really matters. Look at our features right now. We have some values which are in thousands. Some values are close to 0 and 0.5 and 0.1. Now, when you send this to the model, the way all these algorithms work is they'll get biased towards large values. When you send this to the model and say, learn from this, the model says, oh, 3000 versus 0.06. This parameter must be more important. We'll give more preference to this particular band, which is not the case. We want the model to give equal preference to each of the features and then figure out which one is important. So the absolute scale really matters. When you have elevation values, which is very large, and index value very low, elevation will get preferred over this, which is, you don't want that. So one of the techniques that is used in machine learning is called normalizing the data, which is to say, the relative difference is very important. There are 2 pixels. One is 1000 elevation, one is 500 elevation. It's important for model to know that the elevation of this pixel is twice of that other pixel. That information is really helpful. But the magnitude, the absolute value, should be the same range. So typically you normalize the data so that the range of values are between 0 and 1. So for each parameter, you say the highest value of this parameter is 1000, lowest is 0. If the value is 500, make it 0.5. If the value is 800, make it 0.8. And that means all your features will have range of values from 0 to 1. And then the classifier will just say, okay, all of them are equal magnitude. I'll now give equal importance to all of that. So how do you normalize the data? Well, just copy my function. I already have a function that does normalizing of your data. So once you have your final composite ready, say, I have this function that takes an image and normalizes all the bands. Just takes the min and max of each bands, divides the value by the min and max, and the output range you get is between 0 and 1. So once you have the final composite, run the function called normalize, and now your composite pixel values are normalized. And when you sample from this, the features that you send to your model will be normalized values. And once this processing finishes, you'll see that all the values, which were some are large, some are small, all of them now have a range between 0 and 1. So the model will not get biased towards that. There is another technique that some people use. It's called there's another technique some people use called standardizing. Standardizing data is where you change the distribution of data, where the mean is 0 and standard deviation is 1. And that's how you kind of reformat your data. If you want to try this out and see how it impacts a model, in your supplement, we have the folder supervised classification. There's a script for normalization and standardization. You can pick the function either for normalizing data or standardizing data and see which one works best. Most remote sensing people just use normalization. Sometimes if you want to try something different and you want to experiment, you can try standardizing. Some cases, standardizing might give you better result, but at least do the normalization. That's the kind of one very important step for you to get the results. So you can see we ran a normalization function and it finished. The idea for normalization was that the scale of all the features should be the same. Now, when I look at all the input values, you can see they are all between 0 and 1. They all have the same absolute values. And when we send this to the model will say, okay, I'll use those values as input. All of them have the same magnitude. And I will try to figure out which ones correlate best with the output data. Remember, there's still the difference between relative values. If the two values were relatively different, they still have the same separation relatively, but the absolute scale of the value has been reduced to 0 and 1. Now, when we have all of this, so we've done 4 things. We've added a cloud mask, we've added the spectral indices, we have added the other data sets that might be helpful for the classification, we've normalized the data. And now we have our training features, which are ready to be used by the model, and it'll build a much better model, which has more predictive power to correlate with the class better. Let's see the results of what we've done. I'm going to uncomment all the remaining of the code and say we had started with like 93% accuracy. See if we have improved our answer based on all the stuff that we have done. And you can see now we are up to 96% accuracy. We have improved our accuracy by a few percentage points by applying all those techniques. At 93%, we were still very high end of the accuracy. So sometimes when you do things, you say it didn't move much. But if you are doing a large scale classification with thousands of training samples, you typically will have around 75 to 80% accuracy. Doing this thing will push you up by a few percentage points, and that's quite helpful. So again, to recap, Earth Engine allowed to combine multiple data quite easily. Just a matter of adding those as image bands. And when you sample from those, they'll reproject and resample to the same scale that you're sampling from, and you'll be able to extract them as features. So feature engineering becomes very easy. And that's the reason Earth Engine's data model is uniquely suited to do supervised classification. Doing this kind of stuff would take you literally months to build this, versus it's an iterative process where you just add some data, run it, check the accuracy, and then you can decide which features to use. Let's do our next exercise, 3C. Vigna, you can explain.
So then this exercise, we want to improve the classification that we did for exercise 1C. So I hope you have this exercise 1C solution saved with you. We just want to improve that basic classification by adding this function which calculates indices and adds bands such as NDVI, NDBI, MNDWI, and BSI to the original bands that Sentinel has. So you can just copy this function, you can go to your exercise that you have done classification for, and you have to paste it before creating a composite here. So you just can, or you can just paste the function anywhere of this, and you will have to add this function to the composite. So you can say, you can override the composite. So say composite, add indices, and apply it on the same composite. So it will be applied to your composite, and you will see additional bands along with your original Sentinel bands. So try this one, copy the function and update your composite so that you will see these bands. Apply the function on composite so that you will see the additional bands of indices along with the Sentinel bands. After that, you already have the script to do the classification. So it will, if you will run the script after adding this, you will see the classification and it will be the improved one. You can see, if you remember, you can just visualize some changes if that happens after improving your script.
The idea is how we just learned how to improve classification. Let's just try it out on the exercise that you did. You did a classification for your region of interest. And maybe if you're not too happy with it, doing this will give the classifier more information and your classification should improve. We'll now learn how to overcome one of the most annoying errors in Earth Engine. That is when you run some computation and you're trying to see your results or see your chart or trying to see the image, and it keeps computing, And ultimately, you may see errors like this. You may see errors which are displayed computation timed out. Computation timed out. Here, I'm trying to print the confusion matrix. It says computation timed out. I can't see my computation matrix, confusion matrix. I'm trying to print the accuracy. It's not allowing me to print the accuracy because it's computation timed out. The reason for this is not because Earth Engine cannot do this. It's because Earth Engine is saying that I need more than 5 minutes to compute this. This environment of code editor is best suited for interactive computing. You run some code, Earth Engine will give you the result. If that computation doesn't finish in 5 minutes, it defeats the purpose of this interactive computation. Whenever you get this error, the way to interpret this error is Earth Engine is saying, I cannot compute this interactively. Please export the result. And that's what we want to learn. So whenever you see a computation timed out error, the way to overcome this is you have to say Earth Engine is saying me to export this, and I'll export my result. This allows Earth Engine to run this computation not in the interactive mode, but the batch computation mode. Earth Engine offers this another mode of computation called batch computation, where it gives you more resources. Let's say per each user gets some quota. We don't know the exact numbers, but let's say we assume we have X number of machines that is available to you. And when you click the run button, your computation will use those X machines. If those X machines cannot finish this in 5 minutes, you'll get this error. When you export this data, you are using the pooled resource, all of the machines that Earth Engine has access to, and it's going to use that. You may get 10x or 100x number of machines, more memory to execute your task. And it can run for as long as it takes. If it takes 1 hour to run, it'll still run, and the results are done, you'll see the exported result. So whenever you are having a more complex workflow, so here we have a very complex workflow. We're taking images, we are doing cloud mask, we are computing indices, we are computing slope and elevation, we are normalizing the images, and we are training a classification model, and we are doing accuracy assessment. Like so many things we're doing. And Earth Engine is saying, sorry, I cannot do this in 5 minutes. You can export the result. I'll compute this using more resources, and then I'll give you your results. So let's see how we can export the result. Here, we're going to teach you one of the most important skills that you need to learn, which is not intuitive to beginners, is let's say you're trying to view an image and it's timing out. It's simple, you can export the image and you can see the result. But what if you're trying to print a confusion matrix, or you just want to print the accuracy and that number is timing out? Remember, we're just trying to print the accuracy and that's timing out. How do we export a number? How do we export a confusion matrix? How do we export arbitrary data in Earth Engine? If you see the documentation, Earth Engine allows you to export images and tables. There is no export confusion matrix to drive. There's no export number to drive. Right? So if I'm trying to print a number and that's timing out, how do I export that? Well, the trick to do this is you can export anything as long as you convert it to a feature collection. Once you convert something to a feature collection, you can then say, I can export a feature collection using export table to drive. And then I'll see the results. So let's learn how to turn any object into a feature collection. Let's say we want to export this number. I want to export this number, which is timing out. So I'll save this into a variable. I say I want to export this number. I want to export this XPS number. And can't print it because it's timing out. First thing, we want to convert to a feature collection. What's a feature collection? A feature collection can be created from a list of features. So if you have a list of features, that is what a feature collection is. Okay, so we understand that. What's a feature? A feature is nothing but some geometry and some attributes. That's how you create a feature. Once you create a feature, you can create a feature collection of it. Now, what is the attribute? Here we have this geometry. What is the attribute? Attribute is nothing but a dictionary. So now we know if I want to create a feature collection, I can create a list of features with geometry and some attributes, which is nothing but a dictionary. So let's turn this number into a feature collection. So I'll say I want to create a feature collection, e.feature collection, which is nothing but a list of numbers. I just have a list of features. So I have a list, and I can say I just have one feature. So now I have an empty feature collection. Let's fill out these features. What's a feature? A feature is geometry and attributes. We are just trying to export a number. So this number doesn't have a geometry. So we'll say it's a null geometry. This doesn't have any geometry. Attribute is just a dictionary. So we can define a dictionary saying, I will create a dictionary with a key called accuracy, and the value is the number that we want to export. So now I have a feature collection, which is, we just remove this print statement here. So I have a feature collection, which is now containing one feature with no geometry and one number, which is the accuracy. It may run, it may finish computation, or it may time out. I don't care, because now since I have a feature collection, I can export it. So now let's export it. So let's say export table to drive. And we can say I want to export this number feature collection. Description will just say accuracy export. Folder, I like all my expos to go into this folder Earth Engine. File name will just say accuracy. Format you can choose. This is just a text data. You can export it as CSV. Now when I run this, I don't need to print stuff. I say I have this number I want to compute, but I want to compute it as part of an export. So I can run this, and this will now run in the background. It'll take however long it takes, and I'll get a CSV file with just one column containing with accuracy with the number. Sometimes you'll see that when you export something, it finishes in 1 minute. And you might say, why it was timing out when I was trying to run it? Because export has much larger pool of resources, and it can run faster with more memory and more compute. While it's exporting, we can also export other things. So for example, we have this confusion matrix that we want to export. So I want to export the matrix as well. Now this confusion matrix is this object of type EE confusion matrix. And you can't export objects like this as CSV. So if you want to export this, we have to convert this into some text. So this provides this function called .array, which will just turn this into a list. And we can use that to export this. So we can say, now I have converted this into a list. I can now export this and say, along with accuracy, let's just export the matrix. And we'll say, I'll run this and export this. So when I run this, this will also export the confusion matrix along with this. And now let this go on, and it'll take however long it takes. And once it's done, a new file, a CSV file will come in Google Drive, and it'll show me my results. You can see my export finished. It took 2 minutes. Let's see what that export looks like. I'm going to open this in Drive. It's a CSV file with just one number. It says, I have a CSV file containing this one column, accuracy, 96%. So now I was able to export this number as a CSV file by putting in a fake feature collection. Like a hack, but that's a recommended approach. If you read the user guide, it'll recommend the same thing. Turn any object into a feature, put it in a feature collection, and export that. That's a way to export arbitrary objects. So we now know how to export images to Drive. We now know how to export numbers and confusion matrix to Drive. We also know how to export feature collections to Drive. Again, I want to show you the second export that we had started, which is the confusion matrix one. So if I look at this CSV file, you'll see that this contains my matrix as text. And I can take this and put it in paper or do whatever. One of the recommended approaches that you want to follow when you're building something very complex and large like this, when you're working on a real world project, you don't want to build a script that does everything from scratch every time you run it. In this case, what's happening is whenever I run this, it's saying I'll start with Sentinel images. I'll do the cloud mask. I'll compute the indices. I'll compute elevation and slope, and it's doing everything every time. That means if I change something, let's say I want to try building a model with 100 trees, and that means it has to do everything again if I want to change a few things. Of course, I can export this and I'll see my results 10 minutes later, but that's not very efficient. The recommended approach for building more complex workflows is you split your scripts into logical parts. You do part one. Let's say part one is creating a cloud-free composite. So you start your script here and you come here and say, my collection, I have applied my cloud masking and I have my composite here. At this point, say I have my composite, I'm going to reuse this composite when building my model and trying different things. Can I just pre-compute this? So at this point, I can just say export this composite. And don't export this as an image, because when you have an image, you have to download it and upload it to Earth Engine again. Instead, you can export it as an asset. Earth Engine allows you to export data as assets. So if I look at my export function, I can export an image to an asset. When I use this function, this image will go back into Earth Engine in your Earth Engine storage. Once it's exported, it has pre-computed the value. It already knows the value. And it might take 30 minutes, it might take 1 hour. You have your asset ready. Once it's there, you can even share it with your colleague and say, hey, I've done part A. You take this and do part B. Or you can say, I want to further work on this. Start a new script, import the asset. Okay. Remove all of this. Say, okay, now I imported the asset. I don't need to pre-compute this again. I have it pre-computed. I don't need to apply cloud masking. Now I will compute indices. I will do my other data. I'll normalize the image. Once it's done, export the normalized image. Now all of the stuff is, we can export this. So now we export this. It'll take maybe another 30 minutes, an hour. Once it's done, you import this. And that means in the next script, you start from here. You already finished the computationally intensive stuff. Now you say, I will do the test train split. I'll sample my composite and I'll train a classifier and classify the image. At this point, maybe you want to export your training features. This is a feature collection. Export this as an asset, import it if you must, or you can export classifiers. So once you have a trained classifier, you can export classifiers now in Earth Engine. So I can say export classifier to asset. I'll export my classifier. In the next script, I'll import my classifier and then classify the image and then continue that. And that means if I want to build a new model with different trees, I don't have to pre-compute all the previous things. I can just start from my imported asset, change it, and your script will run in just a few seconds. It'll really improve your experience with Earth Engine, where you can tweak things and see the result immediately. In case you say, I want to go back and change something, go back to your A script, change stuff, export it, and then the rest of the script will work. So the recommended workflow is to split your workflow into logical parts and export stuff at intermediate step. This will reduce your memory consumption. So if you're faced with user memory limit exceeded, one way to overcome this is rather than trying to put everything in one step where Earth Engine has to compute everything on the same machine, you are now splitting the computation. So it uses less RAM at each step and it's pre-computed. It doesn't have to compute this again. And that'll allow you to overcome the error. This is one of the main things that allow you to scale your workflow. I have recommended this along with some other tips in our course material here. So in the course material, we have this debugging and scaling analysis section where we say this. It's the same thing here, saying for complex analysis, break down your workflow into logical steps. Create a composite, export as an asset. Import the exported, do your model building. See, import the classified image and do the accuracy assessment. So doing this will really help you scale your analysis and improve your experience in Earth Engine. We have not yet learned how to export stuff in Earth Engine as assets. So let's learn about how to export images as an asset. That's your exercise. Before you dive into exercise, I want to explain one concept. When you are exporting images into GeoTIFF files, you just go and export the pixels. When you're exporting images to Earth Engine says, okay, to allow you to work with these images better, I'm also going to compute all the pyramid tiles. I'm going to compute this lower resolution versions of this asset to allow you to zoom and work with this data better. That is the concept of the pyramids that we learned when we learned about scale. I want to go back to that. So when you export your classified image or your Sentinel image to Earth Engine back, Earth Engine will say, okay, I'll have my original image, I'll export that. Along with that, I'll compute the low resolution version of this style. I'll compute a 20-meter version, a 40-meter version, 80-meter version, and so on. And those will be stored alongside the image. Earth Engine will use this whenever it's required to display this image or do the computation at a different scale. When you're exporting this data, your image, 4 pixels will be grouped into a single pixel at the next pyramid level. When you have Sentinel images, that's fine. So I have 4 reflectances, you're going to get an average value and create a new pixel. The default way it does this averaging, this computing a new pixel, is average, which is fine for most cases. This is called a pyramiding policy. How should I combine pixels into a larger pixel? This is a problem when we're exporting classified data. Let's say I have this classified image that I'm trying to export. I have 4 pixels, which then need to be combined into another pixel. My class values are like this. I have this pixel class 1, this pixel class 1, this pixel class 1, this pixel is class 2. When this is combined and a larger pixel is created, Earth Engine will say, if I don't specify the pyramiding policy, it's average. So the value will be something like 1.4 or something, right? It'll be a fractional value. So when you inspect the image, you say, your class is 1.4. Well, that doesn't make sense, right? I have a discrete image. Class has to be either 0, 1, 2, or 3. It can't be a fraction value. So when you have a discrete images, classified images, and when you are exporting that, you have to specify something called a pyramiding policy. The recommended pyramiding policy is something called mode. Mode is the majority of the values in those 4 pixels will be chosen. So instead of kind of averaging this, to say, what is the majority class in this 4? I'll use that as my pyramid value. And we'll keep doing that. In mode, if there's a tie, like if there's this 1, 1, 2, 2, you'll take the top left pixel. And this is just used for creating this pyramid for visualization. When you do the computation, you specify the scale and say 10 meter, well, it'll use your original image. So it doesn't affect the accuracy of your image, but it does affect the visualization of that. So that's why when you're exporting this, you need to specify something called a pyramiding policy. And that is given here, documented here, how those works. We'll see this in action in our next exercise.
So for this one, we have the script where we are doing the process of classification, and you see we are doing all the steps, and finally we have a classified output. We want to export this image as asset so that we can import it back to use in any different script that we want to continue after the classification. So here you can use export image to asset function that we have. You can give all the required parameters such as image, asset ID. Most important, the pyramiding policy, as we understood that it is a classified image and we have to specify it as mode. So you will have to do this and specify region and scale. And a little bit about the asset ID here, that it should be string like this. So for me, my asset ID could be users Vigna P / name that I want to give to the particular asset. So this is how you can specify your asset ID, and this is how you can specify the pyramiding policy. So try this one with all the necessary parameters. You can use the shortcut control space to fill in the function and try and exporting. As soon as your export starts, you can share your script.
Yeah. So if you see on Vigna's screen, she has 2 kinds of asset folders. One is a legacy asset. This is if you're using Earth Engine for a while, you may have a folder like this, users / your username. In that case, your asset path will be users / whatever username / composite. But if you are new user of Earth Engine, you will have a folder, asset folder, which is linked to your cloud project. And asset root will be starting with your project name. So it has to be project / project name, whatever project name is displayed, and the name of the asset. So Vigna, can you click on this test asset that you have in your EE-Vigna P?
Yeah.
Click on it. So you'll see when you have an asset like this, you can see the asset name, projects / EE-Vigna P / assets / test. This is the full asset path. You can just, in your asset path, you can just specify the name of the asset. And when you export, the dialog comes up, it'll allow you to choose what folder you want to send it to. Do you want to send it to your project folder or your user folder? But if you wanted to have a full path, you have to specify either this way, project / your project name / assets / the asset name, or user / your username. For most people, it'll be easiest just to give the name of the asset. You can just say composite, just give that. And when you run the export, it's going to ask you to pick which asset folder you want to use, and you can pick and it'll start exporting. So try this out, see if you are able to start the export with your asset. You've been learning Earth Engine for quite a while now, and we've still not learned how to compute area. This is one of those fundamental things that you learn in remote sensing, maybe in your first week of playing around with some software. In Earth Engine, computing area is not so simple. It requires you to understand reducers and needs to understand how different methods work. But now, after you learned all of the MapReduce skills and you learned how classification works, you are finally ready to learn how area calculation works in Earth Engine. There are a lot of caveats to area computation, so I'm going to cover this in depth so you understand when you get an answer from Earth Engine, how it is different from other software and how can you make it match what you get in other software. So let's dive into it. We started to work on the script 5A, which is on computation of area. Here we have a classified image for a city, and we want to answer this question: what's the green cover for the city? What's the fractional green cover? We have classified the image, we have vegetation class, we want to compute what's the area of the vegetation class and what's the total area. So what is the tree cover for the city? An important question that maybe urban planners want to know. For that, we need to learn how to compute area for both vectors. So we have a polygon for the city. We also have a classified image that we have. So we need to compute how to compute area of each pixel and sum them up to get the total area. Let's learn how to first compute the area of polygon. Here we have a polygon. So we have this feature collection, Bangalore, which contains this one feature with the polygon. We can say I want to get the geometry. So we'll just say Bangalore.geometry. This will give us a polygon object. So if I just print this geometry, you'll see that I have a polygon object, and I want to compute the area of a polygon. Computing area of a polygon is pretty straightforward. If I say want to compute the area, you have a function called area. You can see features or geometries have this area function, which I can use. So I can just say geometry.area, and you can see it takes some parameters, but both are optional. So I can just say, give me area, and I can just print it. And you see some number. Okay? We saw that this is the area. In Earth Engine, whenever you compute area, the answer is always in square meters, regardless of the geometry's projection, regardless of whatever you're doing. The area is always in square meters. I want to know in square kilometers. How do I turn this into a square kilometer? So we'll say area, I want to compute this in square kilometers. I can take this area and divide by 1,000 times 1,000, right? 1 kilometer is 1,000 meters. So I can say 1,000 times 1,000 is 1e6. I can divide by that. I can print area square kilometer. 713 square kilometers. Pretty close to what the actual area is. So that's great. And you say, I've learned how to compute area. You go and compute this, and then you try to do the same thing in ArcGIS or QGIS or GeoPandas. You'll get a totally different answer. It won't be this area. And now you might be thinking, who's right? Is Earth Engine right, or is my GIS software right? The answer is both are right, but they're doing different things. In Earth Engine, when you are computing area, Earth Engine uses its own proprietary algorithm for computing area. Remember, this polygon is on the surface of the Earth. What is the surface of the Earth? Well, we can assume it's an ellipsoid. We can assume it's a sphere. How do you compute area on an ellipsoid? You can actually do reprojection. You can project it on a flat surface and compute area. You can compute area on an ellipsoid. You can compute area on a sphere. There are different ways to compute this. Earth Engine is using its proprietary algorithm to compute area of polygons. It does this so that it can split the computation across different machines and do this in parallel, so it can compute area for large polygons easily. It also uses a different algorithm than most GIS software use. So you get some answer. Earth Engine says it's more accurate than the other GIS software methods. But again, how do you make sure you don't have a bug in your code and you're trying to compare your results? How do you know it's not because of this function, but it's because of some error? So one useful thing to do is when you're trying to implement something that you've done in your GIS environment into Earth Engine, you may want to compute area with the same function that your GIS software uses. If I wanted to do it the same way, Earth Engine gives you another option. where I can say I want to compute the area, but this time I'll fill in all the parameters. It has got these two parameters, max error and projection. You can specify a specific projection that you want to use for your area computation. So you can say, I'll take my geometry, reproject it to the specific projection and use this. So I can say, I want to compute this area in UTM projection. You need to find the EPSG code for this. The UTM zone for this city is UTM zone 43 North. The EPSG code for this is 32643. How did I find this? Well, you can just search on epsg.io, look at the EPSG code. If you're using software like QGIS, you can just search in QGIS and it'll show you the EPSG code for the same. Let me just show you where you find EPSG code. While QGIS is opening up, I'll explain. So when you are doing reprojection, you can do a precise reprojection from one geometry to the other. It's a mathematical transform. Again, for Earth Engine to do it at scale, to do it fast, Earth Engine says, if you allow me to tolerate some error in the reprojection, I can do it much faster. So Earth Engine expect to specify a non-zero error tolerance in meters. You can give a very small tolerance like 0.1 meters, which is very small. So now I have my area. I'll do the same thing here. And let me print this. See, I got a different answer. When I use UTM projection, I got the area of my polygon as 711 square kilometers. Now, if you do this in QGIS or ArcGIS, you will get exactly the same answer. If you reprojected your polygon into UTM and compute the area, this will be the exact answer. So this is one way when you're trying to implement something in Earth Engine, always specify a projection so that whatever answer you get will match your GIS software. Now, let's say this is the area of the city. Let's say I know I want to use the Earth Engine method of computation. So this is my area in square kilometer for the polygon. I want to compute what's the area for vegetation. So I want to compute area of vegetation. The way to do this is first extract all vegetation pixels, calculate area of each pixel, and then sum the areas of all pixels in the region. And that's how you compute area. In Earth Engine, this is a three-step process if you want to compute the raster area. First, you need to have a binary image, ones and zeros. Ones is the place where you want to compute this area of those pixels. Then you compute the area of each pixel. And once you have area of each pixel, you can sum up all the pixels and there'll be a total region. Let's do this a step at a time. We have this classified image and we want the values of the pixels are 0, 1, 2, 3, the same classification that we've been using. So the class 3 represents vegetation. How do I select all pixels where the pixel value is 3? It is similar to a filter, but you're applying this filter on an image. Remember, filters work only on image collections. If you want to select pixels from an image, then you need to use something called Boolean operators. So you have conditional and Boolean operators. These are like filters, but they work on images. So the operators look like this. I want to select pixels which are 3. I can use .eq 3. This will check this condition against each pixel. If the condition matches, you'll get 1. If the condition doesn't match, you get 0. So the output of this will be a binary image. Let's take a look. So we have a classified image, 0, 1, 2, 3. We have a condition, classified equal to 3. Wherever this condition match, the output value will be 1. Wherever this condition didn't match, it will be 0. So now we have a binary image. Some pixels are 1, the white ones are 1, which was vegetation, the rest all are 0. So remember, when you want to extract pixel values and you want to select, don't apply a filter. Filters work only on image collections. If you want to do this, use EQ, GT, GTE, and so on. Those are the Boolean operators. Okay, so now we have a binary image. Let's compute the area of each pixel. In Earth Engine, there is this function called eImagePixelArea. This is a function that computes the area of each pixel. So you want to use this function to compute the area of each pixel. You might be thinking, in a GIS software, you don't even think about this. So, well, it's a Sentinel-2 image. Each pixel is 10 meter by 10 meter. So my area is 100 square meters. Simple. But Earth Engine says, well, that's not the case. This image is on an ellipsoid. All pixels are not equal. As you go up the latitude, pixels are smaller depending on the projection or the unit you use. So all pixels will have a slightly different area depending on the pixel size, because as you go up the latitude, the pixels will become smaller. So to do this accurately, Earth Engine provides you with a function that computes the actual area of the pixel at the resolution you want. So we compute the area, we say eImage.pixel area. This is the function to compute area of each pixel. We said we now know the area of each pixel in the image. We'll multiply it with the binary image. We'll say whatever 1,0 image we have, we multiply it by this. That means in this region, wherever the pixel was 0, the area will be 0. Wherever the pixel was 1, the value will be the area of the pixel. So now we know the area of each pixel in the image. The ones that are not vegetation will anyway 0. So now we have computed the area of each pixel. We now finally sum all the pixels in the region. How do we sum pixels in the region? Anybody can tell me what function would I use to compute the sum of all the pixels in the region? So reduce region is the function. Autofill for all the parameters. What reducer we want to use? We'll say reducer sum. Geometry is the geometry. So this is the region that we want to select the pixels from. Scale 10 meter. So it will run at 10 meters. Whenever you have a function, and if you're doing a large region, you may have to specify a max pixel value. So let's just specify that even if it's large area, compute that. And if for a very large region, if you get a computation timed out or tile memory error, you can set a tile scale to be a higher number that allow you to run the computation with much more number of machines. Don't set this the first time, only set this when you get an error, and then your reducer will use more machines. Let's run this. So now it will give me the sum of all the pixels which were 1, which is the vegetation. When you run reduce regions, you'll get a dictionary, which will give you one value per the band of the image. This one has only one band, so I'll just get one value, which is the area of the pixels in the region. So this is the value of the sum of all the pixels in the region, always in square meters. Let's extract this. So this is a key with the dictionary with one key called classification. So I can say I want to extract this. I can use the get number function and say get number classification. That's the name of the key. The key will be the name of the band. Since we use this classified image, the name of the band is classification. So now we have this number, which is the area of this region in square meters. I can go and divide it by 1 is 6. And that will be the area in square kilometers. So now we have computed the area of pixels in square kilometers, which is vegetation. So this is the total area of the city. This is the area of vegetation from our classified image. So convoluted process to compute raster area in Earth Engine. But again, this is set up this way so that it's the most accurate way to compute area, and also it scales. It uses MapReduce to divide your computation. So if you want to compute area of an entire country, you can still use all the resources. The question is, I did this for one class. What if I wanted to do it for, let's say, class 2 or class 3, or class 0? I could do something like this and say, I'll do this for class 0, write down the answer. I'll do this for class 1, and I have to run it 4 times. Do map on that. Well, you can do this. Certainly, you can do it 4 times, or you can do this in a loop inside of a function. Earth Engine provides you with a better way. The better way is something called a grouped reducer, where instead of running a reducer sum, you say, give me a sum, but group it by the class value. So you can do this in a single computation. So if you want to compute area of all classes, you can use a group reducer. I want to show you the script in your supplement. In your supplement, we have the section supervised classification. There is a script here calculating area by class, which shows this very example. We take the same image and say, now, instead of doing this for each class, we'll just do this together. So if you want to learn more about group reducers, read my article. If you want to see the implementation, it's similar. We have a pixel area, we add the classified bands, and then just do reduce region with a group reducer. And now we just get answered, we get all 4 classes together, and we can create charts like this. We can create a bar chart of all the classes, we can create a pie chart, and so on. So if you want to know how to do this, in a single pass. Look at the script here. Let's do a last exercise of the module, exercise 5C. Now you can explain.
So for the exercise here, we want to compute a percentage green cover of the city. So this is the same script where we have Bangalore city, and from the geometry, we are calculating area of city, and we are also calculating area of vegetation here. When we have this both, we just need to calculate the percentage. So we have city area in square kilometer, we have vegetation area in square kilometer. Just get the percentage green cover for the city and print it.
So when you print it, you'll get some number like say 25.4267%. So first try to do this. Bonus points if you try to figure out how to print the number, rounding off the number to 2 decimals. So let's say we have this long fraction, how to round off the number to maybe 2 decimals or 1 decimal. See if you can figure out the API function for doing this. It's not that straightforward, but first try to print the fraction. And then once you figure out, see if you can look in the docs and see if you can find a function to round off the number to. Let's do exercise 5C in module 3. We've been doing machine learning and supervised classification. You learned how to collect training data, train a classifier. We learned how to classify the image. We did accuracy assessment. We still haven't completed the full workflow for doing supervised classification. Remember when we chose this random forest model, we chose number of trees as 50. And we said we'll tune that later. So once we have something working, we have a decent accuracy, we have our model. If you want to improve the accuracy or pick the best parameter for improving the accuracy, we can now tune parameters. So let's learn the technique for tuning parameters. This is called hyperparameter tuning in machine learning. Hyperparameter tuning is the process of figuring out what parameters of a model will work best for your data distribution. Again, there is no theory, there is no algorithm that says, okay, given this data distribution, use this parameter. If your data set is like this, use 50 trees. If the data set is like this, use 100 trees. It really depends on your data and what you're trying to do. So these parameters will determine how the model learns and performs, and different parameters will give you different result. So it is, if you want to have the best results, you have to make sure the parameters are tuned to your particular data set distribution. And as with everything in machine learning, how do you figure out? Well, you just try different things. So this is a quote that just summarizes what machine learning is. Machine learning is just trying random stuff, trying all the stuff and see which works better. The trick is if you do it fast enough, that's machine learning. So the trick is how do you try different things using code instead of trying manually. So here we say, I don't know what is the optimal number of trees. Let me try building a model with 10 trees, 20 trees, 30 trees, 100 trees, 500 trees, 1,000 trees. I'll try all numbers. And I'll pick the number that gives me the highest accuracy. That's what hyperparameter tuning is. The most commonly used method, the algorithm for hyperparameter tuning is called grid search. Well, you say, I'll take a parameter. What is the valid range of the value? Number of trees, well, usually random forest has 10 trees to maybe 200 trees. That's kind of the range of the parameter. We'll try all the values in the parameter. There's other parameter called bag fraction. How many of the training samples you want to use for training, randomly selecting for each tree. So if you have 1,000 samples, you want to use 500 samples for each tree or 100 samples. That value is from 0.1 to 0.9. Well, we'll try every value between those. So you figure out the range for each parameter and then try all the possible values between those range, and then pick the model that gives you the highest accuracy, whatever metric you're using. Say I want to use overall accuracy, or I want to use F1 score, whatever metric you're using, whichever combination gives you the highest value, just use that. This is the last step in your model. So once you've done everything, you say I have something that works fine. Why not I optimize my model so I get the highest accuracy? I've done everything else. So run this as the last step. And once you run this, you'll find the optimal number of parameters for each, optimal values for each parameter, and just replace them in a model, and then you're done. Export your results. We have a script in the supplement. Let me show how that works, and then learn a little bit more about how the algorithms work internally as well. So this is our standard classification workflow. One of the things that you can do is once you have trained a classifier, every classifier that Earth Engine has, or most of the classifiers have a method called explain that tells you a little bit more about what the classifier learned during training. And that's got some really useful information. Let's see the output of this explain. When I call explain, you'll say, okay, these are the classes. there's something called importance. When we have all these features that we used during training, the model will get a sense of which parameters were important. If you added some new band and we didn't help in the classification too much, the importance of that band will be low. If one band was really used a lot for classification, the importance will be high. This gives you a sense of which parameters were important for your final output. These values are ranked from highest to lowest. So the highest value is the most important parameter. The lowest value is not important. They are not percentages, but you can normalize it to a percentage, and you can create a chart like this. So again, this code shows you how to create a chart like this, where you can say, show me the importance of each feature. And looking at the chart, you can say, in my classification for my city, band 3, band 2, BSI, MNWI, and DVI were more important. Slope didn't really play a factor. So we can just remove the slope band. This is also a great way to test what features might be important to your model. So when train a classifier, print .explain, and you'll be able to see those values. We have a trained model with, say, 50 number of trees, but which may not be optimal. So we want to test different number of trees. How do you test different number of trees? We say the range that we want to test is from 10 number of trees to 150 trees at interval of 10. So this will create a list of trees from 10, 20, 30, 40, all the way to 150. We have a list. We can map a function on this and say, for each of this tree value, create a model with that number of trees, train it with your training data, test the accuracy of the validation fraction, and return the accuracy. We'll run this 15 times, one for 10 trees, 20 trees, 30 trees, and so on. When you run this, you can create a chart like this. You'll get a chart that looks like this. So we ran this model 15 times with different number of trees, and this is what we get. What is the optimal number of trees I should use for my model by looking at the chart? What do you think? How many trees should I use? So there are, at 10 number of trees, I get 93% accuracy. By changing nothing, just simply setting at 20, I get a higher accuracy. At 30 trees, I get 96% accuracy. At 50, I also get the same accuracy. But with 50 trees, I have a lot more computation to run. So why would I go with 50 trees with the same accuracy? So I'll pick the highest accuracy with the lowest number of trees. And I'll say, I've tuned my parameter. Let me just replace 30 in my model, run it. I'll get 96% accuracy. So this is how you tune the parameter. If I look at the model, let's look at my random forest. This one has so many different parameters. So we say we can choose the number of trees, but there are other parameters, variables per sled, mean leaf population, back fraction, and so on. There are some defaults, but what if we want to tune those as well? So let's try tuning multiple parameters together and see how that works. So we want to tune both number of trees and back fraction. Back fraction is when each tree is trained, it selects a random subset from the samples and trains a tree. Then it takes another random subset, trains a second tree, and so on. So when we say we can do from 10% to 90% at 0.1% interval. And again, we'll try different trees. So now we can map a function within a function. So double for loop, where we say for 10 number of trees, try a model with 0.1, 0.2, 0.3 to 0.9 back fraction. Then take 20 trees and try the same thing. So we try all the combination of these two parameters, train the model, compute the accuracy. If you don't like accuracy, compute F1 score, whichever makes sense for your purpose. Now, at this point, the computation will start getting more complex, which will not finish in 5 minutes. So if you're doing multiple parameters, you can say convert this to a feature collection and then export this to a CSV. So we have an export task. We can run this. I just started it a few minutes ago and it's finished. Once you try exporting this, this is what you'll get. So say I have tried tuning these two parameters and I get results like this. With 0.1 back fraction, 10 trees, I get this accuracy. With 10 trees, 0.2, I get this. So now you go and pick the highest accuracy that you have and pick those two parameters. And that's your answer. That's how you tune two parameters. You can also do it automatically. If you have some bit of code which says, just takes the results that we exported, get the highest accuracy and back fraction, and automatically create an optimal model here. So you don't have to manually look at the CSV and do this. So I can just run and say I have my final model with optimal number of trees, optimal backfaction, and then classify this image and export my final classification. So this is how you tune parameters. Well, you want to tune the third parameter, update the code, run it. You don't even need to look at the code, take your final classification, export the result. You will have the best classification that this model can perform. And again, this is all done through code. So do this as the final step. And again, with a lot of machine learning, most of the time is spent in data collection. Once you're done, just run this piece of code one after the other, and you have a final result. One of the things I also want to tell you is, remember when you printed classify.explain, this also prints in the actual trees that it print. So that's kind of useful to know. Remember, we tried our first model with 50 trees. When you say classify.explain, it'll actually show you each tree, what that decision tree looks like. So the way to read this is the first tree. At the root, it's checking whether the band 3 is less than 0.12. If so, the class is 3. If the band 3 is greater than 0, do this. NDBI is less than 0, try this. If NDBI is less than 0, try this. So you just figured out all the different thresholds for different bands and just built this decision tree that allows it to make the decision on what classes. And you can see this is the first tree. This is the second tree. The second tree uses, because it was randomly initialized, you will get something different and so on. But again, you can actually see those trees and just understand how the model works internally. We have implemented our classification workflow. We have tuned parameter, and we said we are happy with our result. If you still want to improve, you can go and collect some training there. But let's say I'm done. I have enough accuracy. I visually assessed my result. I'm done. I'm finished my project. What do I do now? Well, before you export a final image, it is useful to do some post-processing. So let's learn some of the common post-processing technique you can apply to improve your results and remove the noise in your final classification. So we're going to learn about the post-processing techniques for improving your classification results. Now, one of the problems with this pixel-based classification is that each pixel is classified independently. The random forest model that we've trained, it'll get some reflectances and some band values, and it'll predict what's the class of the feature. It doesn't know what is around the pixel. So each pixel is classified independently. And because Earth observation data is noisy, your classification also may have noise. It may be that you have a water body, every pixel is water, except this one pixel which is misclassified as vegetation. If the pixel had spatial context, it might say, okay, I'm surrounded by water everywhere, I'm likely water, but it doesn't know that. So it'll have noise there. So we can apply some post-processing to say, if you are surrounded by all water pixels, just remove that pixel and classify it as water. So you can kind of remove that salt pepper noise on that. Two main technique. We can do unsupervised classification to say, I have this classification. I'll cluster my input image into clusters. Each cluster has the same kind of pixels. So if I have different kind of classification within that cluster, I'll replace the value of the cluster with the majority value. So in that cluster, after my classification, 100 pixels were there. 98 of them are water. 2 of them are not water. I'll replace everything in the cluster with water. That'll give you some smoothing. Another technique is connected pixels, where you say, find the number of pixels which are connected to each pixel. So this pixel has 10 other pixels connected to it, or this pixel has no other pixels connected to it. You find the number, and you say, I'll remove the pixels which are not connected to other pixels. So I have a water pixel, which is isolated. I have a whole forest, and there's one bare pixel in between. It's not connected to other bare pixels, and I'll remove those. For clustering, we can detect objects using any of the clustering techniques, and then remove the values with the majority of the values. When we do the post-processing using clusters, you detect clusters and replace the value of the cluster with the majority value. So whatever are the non-majority pixels, you replace it with the value of the majority pixels. We have the script in the supplement. I'm going to show it in a second. But let's learn about other techniques. So again, if you say I have this original classification, and if I apply this clustering techniques, I'll detect clusters. And for each cluster, I'll replace the value of all the classification to be the same. So I'll remove all the outliers. And you can see this is what the result would look like. You can see it's much smoother. All the noise is gone. If you look at this region, you can see there is some isolated vegetation pixel between this water body that's gone. you have some parameters, the cluster size and connectedness and etc. So you can determine how much smoothing you want and how the clusters are determined. But this is only needed to get a classification result, which makes sense. The second technique we have is connected pixels. There's a function called connected pixel count, will tell you how many other pixels are connected to this pixel and will detect isolated patches and say any patch which is less than this particular pixel numbers will be replaced with the surrounding value. The function we will use is called focal mode, which will say in a neighborhood, replace the center pixel with the value of the surrounding pixels. Here's the example. If you have this classification and you do with connected pixels, you get a result that looks like this. You can see it's reduced the amount of salt, pepper noise, and the results look much nicer. Before I show this, so again, this is just showing the comparison of the two techniques. You have the original image on the left, the center one is the cluster one, the one on the right is the connected pixels. So again, you can pick the technique that works for you. We have the code that I want to show for both of this technique and the parameters that you use for computing this. So I'm going to show the script from your supplement, supervised classification, post-processing results. Let's go through the code to understand how both of these techniques work. The first technique is by clustering. So we use some clustering algorithm. Here we are using SNCC. We say, take my composite image, select all the bands, and cluster the image based on the band values. So all pixels which have similar values in all 12 bands will be clustered together. And we find these clusters. You have all of these parameters. Read the documentation to see what those mean. And you can adjust those to see if you want bigger clusters, smaller clusters, and so on. Once you have the clusters, you can use this function, reduce connected components, and say, given these clusters, replace the value in the cluster with the mode value. Use the e-reducer mode, which is the majority value. So within each cluster, whatever the classified values is there, will be replaced with the mode value. And this is your output for that. The second option is to get the connected pixels and remove pixels which are not connected to as many other pixels. The function connected pixel count will give you an image where each pixel's value is the number of pixels it is connected to. How does it work? Let's say there are two parameters. Max size, how far should I look in the neighborhood? So for each image, each pixel, how much of neighborhood should I get? And again, we say look up to 40 pixels here. So we say up to 40 pixel neighborhood, go and check how many pixels is it connected to. Second one is, how do I determine if the pixel is connected? By default, it's going to use the for connected method. That is, the pixel, the top, bottom, left, and right are considered connected. The corner pixels are not connected. So if you think about a chessboard, a diagonal line will not be considered as connected. If you set this parameter 8 connected true, sorry, default is 8 connected. So by default, all pixels in all directions are connected. So diagonals, top, bottom, left, right. If you do not want that, if you only want the pixels to be 4 connected, top, bottom, left, right, you can set this parameter to be false. Sometimes, especially when you are converting your results to vectors, setting 8 connected to true will result in some invalid geometries. So sometimes it causes problems. So if you find yourself that you get an image which looks weird, or when you convert your result to vectors and you get some invalid geometries, try setting this parameter to false. You should have a much better result. But here, when we use this and we now have each image where it says how many pixels is connected to, it says, I will take all pixels where the patch size is less than 25. Any pixel which is connected to less than 25 pixels, replace it with the value from the surrounding. And this is a kernel operation which says, look at the radius 10. What are the majority pixel values around you, around 10 pixel radius? Replace your value with that if you are connected to less than 25 pixels. So to control the amount of smoothing, you can control this parameter and you can control the neighborhood. Both of this will control how much smoothing you want, more or less, and you'll get the result. And finally, once you're done, you can export the result to see the output of your post-processing. I want to explain your assignment 3. You are ready to do your last assignment for the class. Let's learn what is your assignment 3. In your assignment folder, we have the description of the assignment 3. This is very simple. We've covered our supervised classification module. All of you attempted supervised classification for a city. You didn't have much time. You dropped some points, and we did a basic supervised classification. We want you to take the same data that you worked on, enhance it to create a proper classification for a city based on all the techniques that you learned. So you should definitely add more training samples. Once you have training samples, you can add some indices, all the indices that you want for those 4 classes. apply cloud masking, add elevation and slope, normalize the data, and see the result. This is the bare minimum, but if you have time and inclination, you should also do accuracy assessment. So you have more training samples. You can now split them into training and validation, do an accuracy assessment, and if you have more time and inclination, try applying other techniques that we've learned on adding spatial context and doing PCA and all of those other techniques, and see if you can improve your classification for a city. So try out this assignment. And this is the bare minimum. You have some other scripts in the supplement that will help you. I want to point you to this particular script. Identify misclassified data. So when you do the classification and validation, you say there were 2 samples that you tagged as 0, but it was classified as 1. It will be useful to know where are those points. And you see this in the confusion matrix. It'll be nice to see where are those points, so I can know whether I dropped a point by mistake or was it an actual error that the classifier made. And here is a code that will help you do this. Is using simple filters to say, show me all the points which I tagged as X, but was classified as Y. And you'll be able to see those points, and then you can go and say, these are the misclassified training point with this particular classifier. So I have 12 samples that are misclassified. You can go and check each of them, whether they are really good training samples. Sometimes you made a mistake in your training sample that would have caused that. So you can use this. If you want to know if the points are always getting misclassified, you can also use this code here, spectral signatures, to take each training sample and plot the spectral signatures. If your training samples are all for the same class, the signature should be the similar pattern. By mistake, if you dropped a point on a wrong point, like you're trying to take examples of water, but by mistake you dropped it on vegetation, the signature would be very different, and you'll be able to see that in your example. So you can see for each class, all the points should exhibit the same pattern. And this is also a good debugging thing to say, oh, you can see here, there's this one point which is very different than others. So maybe either it's actually a real different kind of water, or it is a wrong training sample. So these 2 scripts, spectral signatures and identify misclassified data, are a good script for debugging your training samples, which is what the cause of the most bad classifications. So do take help of those scripts in case you have problems improving your classification. We have the same presentation for machine learning. So I want to start and teach you some of the advanced machine learning techniques specific to geospatial science. So when you are working with geospatial data, you want to apply those standard machine learning techniques, you are losing a lot of information. Traditional machine learning models were developed for tabular data. So if you have a table of data, and say I have some columns, and I want to use certain columns as input, one column to predict, and each row will become my feature, and I can train a model that can predict the class based on that. And when we apply those models in geospatial data, what we're doing is we are essentially taking our pixels, turning them into a table and saying that these are the bands, each band will become one column, and we are creating this table where we have some input columns and we are predicting the output column. This works, but we are missing 2 key aspects that sets the geospatial data apart. One is in geospatial data, we have spatial context. We understand that each pixel may be at a different place, and that is really important. Location really matters. If there are 2 pixels, one is closer to a road, one is far from a road, and you're trying to predict something, that distance to road matters. And how do you capture that? What if in your image there is a north-south pattern, and if you sample 2 points from north and south, and they have the same reflectance, the classifier cannot tell them apart. They said they both look the same to me. It might be helpful to add the latitude and longitude information to say, okay, those 2 are separate. I've labeled them differently. How can you separate them? Well, you can figure out if there's a information in the coordinates that will tell you whether this is now north, south, or east, west pattern. So adding the spatial context to your model will really help the model understand the spatial context and improve the classification. How do you add spatial context? We are still stuck on a tabular model. Random forest, decision trees, SPM, all of these classifiers expect a table. So the main trick is turning the spatial context into a table. I'll teach you some of those techniques. One thing you can do is if you want the model to have information about the coordinate where the pixel was sampled from, you can use this function ee.image.pixel.lat, which will add 2 bands to your image. So let's say you have a composite image and you run this function, you'll get 2 new bands, latitude and longitude. And the value of each pixel will be the latitude and longitude of those pixels. So when you sample that point, it says, here are the reflectance, here is the latitude, longitude, and here is your output class. And now the model can learn from lat and long if there's information to learn from. If it doesn't matter, the model will say it's not important, it doesn't help me predict the class better, it'll just ignore that. But it'll help you capture that coordinates if it's important. Second, there's a function called distance, which allows you to compute distance to the nearest pixel in an image or the nearest feature in a feature collection. A classic example that would use this is, say, you are trying to predict house prices, or you're trying to predict urbanization. If your 2 pixels are labeled as urban, or 1 pixel is labeled urban, 1 pixel is not urban, and they have the similar reflectances, but 1 pixel is closer to a road, 1 pixel is really far from a road. The classifier will learn that the pixels that are really far from the road are less likely to be urban. Similarly, if you're trying to predict housing prices, distance to beach, for example, distance to school, those are important parameters. And Earth Engine has this function called distance that allows you to capture that information as bands. So again, in Earth Engine, whenever you want to use any of this thing, you need to turn your whatever parameter you want as a band. So you create a band where each pixel value is the distance to the nearest object. And you can use that information in your composite. Lastly, if you say I have a pixel and I really want to know what's going on around it. So if you have 2 pixels, same reflectance, but one is surrounded by high NDVI, one is surrounded by low NDVI, and you want to use this information to classify them separately. There's this function called neighborhood to bands. So essentially it'll take the neighboring pixels and turn them into bands. So when you sample them, you'll have information about the neighboring pixels along with the pixel value itself. We have a sample code that'll show you how to do all of this and improve your classification. Let's take a look at the script to understand how all of these functions work. In your end-to-end repository, we have the supplement folder. I'm going to show you the scripts from the supervised classification folder in the supplement. Here is the first script, adding spatial context. Let me just print the composite. Comment out stuff and then uncomment it one after the other. So this is the image we are starting with, 12 bands, Sentinel-2 composite. And you said, I just want to learn from that. So when you have your training samples and you sample your image, each feature will get those band values and say, these are our input, try to predict land cover. How do we add more spatial context to it? First, let's see if we can add on this function, e.imagePixel.lat. And you'll see that your composite once you run this function, your composite will have 2 new bands, latitude and longitude. And the value of those bands will be the lat and long of each pixel. So now when we sample that composite image, you see that each training sample has the band values plus latitude and longitude of that particular point. And now the classifier can learn from that. Right? So that's something that you can do. Most machine learning models would use that as input. So feel free to just run that function in a composite before you send it to the classifier. So let's say we have a road network. I've uploaded OpenStreetMap roads to Earth Engine, and this is what I'm using here. And I want to say if my training sample is close to a road, I want to capture that. If it's far from the road, I want to capture that. You can run this function .distance on the road, and what you get is a raster like this, where the value of the raster is the distance to nearest road. And you can add this raster to your composite. And when you sample that, what you get is that in each feature, you'll have one more property called distance. So this point is 74 meters away from the nearest road. If I go to some other sample and say this point is 41 meters from the nearest road, so on. Right? So now I have a property that captures the distance to nearest road. And if there's a pattern, the classifier will learn from that. Okay, so the function here is called .distance, which is the distance to nearest feature collection. And there's also a distance function that works for raster images. If you have a raster saying that this is water versus non-water, it'll say distance to nearest water object, for example. The next one, let's say I have a pixel. I want to know the value of surrounding pixels. So for example, look at in this case, I'm trying to classify this pixel. Let's say there are 2 pixels here, but they are surrounded by different things. How can I capture the surroundings? There's a function here called neighborhood to bands. You can give it a kernel and it'll capture the neighborhood and turn them into bands. Let's see how that works. once you run this, you get additional bands. For example, I've run this function on the NDVI band. So I've computed NDVI. So I get the NDVI of that pixel, but along with that, I get neighboring NDVIs. So I get 8 more NDVI values, NDVI of the left pixel, NDVI of the corner pixel, NDVI of the top pixel, and so on. And all of those are now bands. For each pixel, in the new band will be the value of its neighbor. Then the effect of that is when I sample that image, now I have multiple values of NDVI. This is the value of the pixel's NDVI, and this is the NDVI of the surrounding. And our model can learn from all of that. And if I uncomment everything here, you can see I'm now training a, I'm training a classifier on all of this spatial context because I've turned them into a table. I've turned the spatial context as bands, and when I've sampled my training data, I have all of those information. Each training sample has that information. The random forest will try to use that and say, how can I best use this to predict the class that I need to? And then you'll have your classified image that will be much better than without using the spatial context. You don't need to use all of this. Use whatever makes sense for your analysis and for the project. Next, one of the advanced techniques for geospatial machine learning is how to incorporate a time series. When you're trying to classify an image, sometimes just the pixel value it's not enough to distinguish two different pixels. Most common example for this is crops. Let's say you're trying to identify crop versus forest. They may have the same reflectance if you just consider the median value. They both look green. But now how do you separate them? Or you're trying to separate two crops which both look green. How do you separate them? The way to do this is to incorporate the whole history of the pixel, because the pixel has undergone change during a year or growing season or harvest season, and you want to capture that temporal context in your model so that model can say, hey, these two pixels have different history, and if I learn from the history, I can separate them. How to do this in the Earth Engine or how to do this for machine learning? Well, you have to turn the history of a pixel into a table. Let's see what are some of the techniques to do this. So how do you capture the time series variable as bands in your image? If you convert your time series into bands, you'll be able to use them as an input to your classifier. Two main techniques. One is called seasonal composite. So you instead of doing a yearly composite, you just say, I will take one composite for each season, one for the growth season, one for the harvest season, one for the barren season, and so on. Whatever season makes sense for your crop that you're trying to classify. And then you use information from all of those composites as bands and use them in your classification. Let's see the example for this. Back to your repository in the supervised classification folder, we have a script, seasonal composite for crop classification. We are using the same area that we are trying to classify. This is in south of India. This part of the world, they follow different cropping season, and you need to capture those cropping season to be able to classify the crops in this region better. So you start out the way you do. You start with the Sentinel collection. You apply the filters for the year that you want to classify. You do the cloud masking. After you cloud mask, don't do a median composite. Let's do different composites for different seasons. In this part of the world, they have 3 distinct seasons for cropping. One is the winter crops, there are summer crops, and then there are monsoon crops. So I can take one composite for January to March images, another composite for April to June, and another for July to December. And I can create different composite. Here we just define those months as list and then map a function over it. So we can create one composite for each season. Let's see what those composites looks like. If I go to some region here, you'll see that the landscape looks very different in each of the seasons. This is what it looks like in winter. This is what it's in harvest season. And see, there are changes here. And then in the monsoon season, it's again very green. You will see that it's just totally different. And if we had just done a median composite, we would totally miss that. So now instead of having just 12 bands of information, we have 12 bands of one season, 12 bands of another season, 12 bands of another season. You stack them together. So the function you would use is add bands. You can say take the first season composite, add bands from the second season, add bands from the third season. And now you have this 36 band composite. When you sample your training data from this composite, you'll get 36 values. What the pixel was in season 1, what the pixel was in season 2, and what the pixel was in season 3. And you need to predict the class based on those 36 values instead of 12. And the model will learn that if crop A is growing in the first season, values will be higher here. If crop B is growing in summer, the values will be higher here. And it'll use those relevant bands to classify them. So you're just sending them more information, and the model will learn from those information. And this is how you can incorporate time into your model by just doing seasonal composites. I want to share one example. I've linked to the paper in the slide here. If you're doing any kind of crop classification, do read this paper. It's a really interesting methodology and it shows you the standard technique of how you can do crop classification and incorporate time in your model. I want to show you the chart for the methodology. You can see the chart. They're using Landsat data, and they're trying to distinguish coffee from other crops. So you're trying to map coffee. It's a crop classification. So again, just doing median composites is not enough. So you say, I'll start with my data. I will do 4 composites: dry, hot season, rainy season, dry, cool season, and then 1 median composite for the entire year. So I've now done 4 composites. And coffee has different growth pattern in all of those 4. Different crops or forests will have a different growth pattern. And by giving this information, you are able to then separate out coffee. One of the problems that you'll see, we'll shortly learn how to deal with this, is now you may have 12 plus 12 plus 12 plus 12, 48 bands. And that is too much information for the classifier to learn. So you can compress the information by doing something called principal component analysis. You do this here. So you can say you'll compress the information into less number of bands. You still retain all the information from the 48 bands, but you have much lesser bands to work for. And then you just say extract all the band values at training points, develop a random forest model, do the classification, and you have a final land cover map. So again, this paper employs the seasonal composite technique that I mentioned. And again, they say, okay, we also want to use elevation, slope, and aspect bands. Elevation is really important for coffee. Coffee grows at higher elevation, so you want to capture that for coffee as well. So again, any information that makes sense for your crop that will help it differentiate from other crop can be added here. So we learned about seasonal composite for crop classification. Here we are defining distinct seasons and say, if I want to do seasonal composite, what if I want to capture the full phenology? Maybe there are too many crops and each follow the different growth pattern. I can't distinguish them between seasons. How can I capture the exact phenology and use them for my classification? So that brings us to the next technique, which is called time series modeling. Here you don't create any composite. Here you say, I'll take the full time series of some value and most commonly used one is NDVI because it captures the vegetation growth. So we'll say, I'll take the full time series of NDVI, every observation that has occurred in a year at each pixel, and I'll try to model that with some mathematical formula. So instead of doing composite and getting the reflectance value, I said, I don't care about reflectance. I want to know what was the pattern and can I capture the pattern at each pixel? And if the pattern is similar to a neighboring pixel, then it's the same crop. If the pattern is different, then those two are different. That's called time series modeling. Again, very hard thing to do mathematically and hard thing computationally. Earth Engine makes it much easy to do. There's code available. I'm going to show you the code and now you can run it at scale because again, you don't have to download images. You don't have to extract the time series. You can just run it at each pixel. So let's see how to do this. The script is in the same folder called time series modeling. Here we start with a collection and we apply our filters, apply the cloud mask. Cloud mask is important because you don't want to capture cloud in your data. You want the real NDVI. And once you have your filtered and masked collection, you extract your time series at each pixel. And you can see this is what each pixel look like. This is over one farm. And you can see the pattern from 2019 to 2022, 3-year pattern. And you can see some noise, but you can kind of see the pattern, right? There's a growth and harvest and growth and harvest and so on. If I want to incorporate each image's bands into my learning, I'll have 12 bands for hundreds of images, and that doesn't scale well. So instead of adding bands for reflectances for each image, I'll say, can I just model this using some function? Most of the time, NDVI looks like a sine wave or a cos wave. So can I say, can I fit a sine wave to this? This is also similar to Fourier transforms, where you have any signal and you decompose them into the sine and cos waves. of a particular signal. So can I fit a sine curve to it? And you can fit this. The code is available here. You can just copy paste the code. And once you fit, only parameter you need to change is how many sine waves do you want to fit into. It's a single cropping, dual cropping per year. So per year, how many sine waves you want to model this with. So here we are modeling 2 harmonics per year. And when you run this, you get something like this, that I had this time series. I've now fit sine wave to it. And I know how to describe the sine wave with a formula. I can uniquely describe the sine wave by using phase and amplitude, 2 numbers, and I can model this. And you can do this at each pixel. You can model the time series using phase and amplitude values at each pixel. If you have 2 harmonics, you'll have 2 phase and 2 amplitude values. If it's a one cycle per season, you'll have 1 phase and 1 amplitude value. Now, if you do this at every pixel and you compare 2 farms, which are very different crops, and you just show what the model looks like, you can see the model looks very different because the growth pattern of those 2 farms is very different. And the phase and amplitude value at those 2 places will be very different. You capture the full phenology of NDVI at those 2 pixels by this 2 parameters, phase and amplitude. And what we do when we do remote sensing machine learning, well, we say we have 1 phase value at each pixel. So we have a phase image, we have an amplitude image, let's add it to our composite. And when we sample that, the classifier will say, this is the phase, this is the amplitude, this is the class. And if those 2 are different for different crops, it can separate them. You can also visually see this. If we display phase and amplitude bands as an image, this is what you'll see. You can see this is the landscape, different crops growing in this region. I've taken 3-year Sentinel-2 NDVI time series, fit harmonic time series at each pixel, and displaying the results of phase and amplitude values at each pixel. If the colors will represent those combination of phase and amplitude. The colors at 2 pixels are same, that means they're growing the same crop. The colors are different, they are growing different crops. Once this loads, you will see different farms and different colors. The farms growing the same crop will be in the same color. And now if I add those bands to my composite, the classifier will be able to learn from this. This is a really robust technique that can capture the full phenology, can capture different kind of vegetations. So if you want to separate out grassland, shrubland, cropland, permanent forest, how do you do this? Well, just fit this harmonic time series, take those bands and send it to the classifier. The classifier with the training data will be able to learn from each of this and can separate them. Again, something like this is very computationally intensive, but you can see you can now do this in Earth Engine. If you're doing this for your region, compute this, export this as an asset. And once your asset is computed, you can add it to your composite and do your machine learning with that. The next topic I want to cover is the topic of principal component analysis. When you are adding too much information to your model and say, I have bands for season 1, bands for season 2, bands for season 3, or I have added temperature band, I've added slope in elevation band. And as you add more and more information, the classifier finds it much difficult to discover the true pattern. It has to say, I have 500 columns of information that I need to learn from and predict this class. And each column, each feature is sending a very weak signal of how it is related to the output. So in machine learning, this thing is called curse of dimensionality. If you have multi-dimensional data, the more dimensions you add to your data, the classifier finds it harder and harder to learn. And then if you test the accuracy of a model, if you keep adding more bands to your composite, at some point the accuracy will start going down. So the classifier just can't learn from so much data. So I want to use all the information. The information is important, but how do I reduce the dimensions of the data? So how do I compress all of this hundreds of bands of information into smaller number of bands by reducing the dimensionality? The main technique that you use is called PCA. This is a statistical technique that says, I have this information, can I compress it into information where I retain most of the information that was there in the original bands, but I'll have much fewer bands. The way they do this is you say, I have 2 bands which might be correlated. Let's say I have band 1 and band 2. Whenever the band 1 is 10, band 2 is 20. Whenever the band 1 is 20, the band 2 is 40. Everybody is like this. So I said, why do I need 2 bands? They are all having the same information. They all have this, they're correlated. Whenever this band 1 goes up, band 2 goes up by the same amount. Why do I need 2 bands? I can remove information from band 2 and I can have only the bands which are uncorrelated and I can still retain all the information. And this is the kind of core concept of PCA. when you run PCA, it'll try to extract all the uncorrelated information from your image and give you fewer bands which have most of the information. And in remote sensing, you say, whenever you say, I have 12 band image, I do PCA, I'll get 12 PCA bands. I'll get principal component 1, principal component 2, principal component 3, and up to 12. But most of the information that was there in the 12 bands will be in the first 2 or 3 bands. So you say, I'll not use all the PCA bands, I'll just use the first 3 PCA bands and use that for my classification. I'll still retain like 99% of the information. So my classifier can still separate out and do all the work, but it has got much fewer dimensions to work with. Let's see how this works in practice. You have the script in your supplement. So here, let's say we have this 12-band composite. And we want to use this. Let's say you have a seasonal composite, you have 4 such composites, and you want to use them for machine learning. And you don't want to send 48 bands to your classifier. You want to say, I have this 12 bands. Some of these bands are correlated, right? There's a red band and a red edge band. Or there is, this SWR1 and SWR2. Most of them will be having some information which is duplicate. Can I compress that? So we have a function written for you here called PCA. Take an input image, return the PCA for that. So here we just call the function on the composite. We return the PCA image. Let's run this. So we take this 12-band image, run the principal component analysis on this, and you get 12 principal component bands. If we compute the variance that was captured by each PCA band, the output of the analysis says the first band of principal component captures 68% of the variance that was present in the 12 bands. The second band captured 22%, third band 5.6%, and so on. The 12 band doesn't have 0. It has still some information, right? But you can safely say, I will just use first 3, and I've captured like 98% of the variance. And I'll send only the first 3 PCA bands to my classifier. And my classifier now can work with much richer data, which is uncorrelated. Each band will have unique information, and it'll be uniquely correlated with the output. And it just performs much better. If I just take the first 3 PCA bands and take that image and display this on the map, you'll see how the image looks. So at the bottom is the RGB image, and on the top is the principal component image, just the 3 bands. This is the image that was captured by Sentinel-2, and this is the information that is captured in all 12 bands. You can see it correlates quite well with that. It also has so much information in this, but now you have only 3 bands. And the classifier will only see these 3 bands, and it'll try to use that for your classification. So you do the PCA, and at the end, you only take the first 3 PCA bands and then add that to your composite. In my experience, this is the magic bullet to fix your classification issues. Every time there's a classification problem, you do PCA, suddenly your accuracy jumps 5%, 10%, and so on. So this really helps the model learn much better. You can apply this in all contexts. For example, if you want to add texture to your image, you compute texture, you get 17 bands. You don't know which one is important. Do PCA on those texture bands, send only those 3 bands to your composite. You're doing seasonal composite, for each season, just do PCA for that season and add that to your main composite. And that really helps the model learn from the features that are really important, and you should see much improved accuracy. Okay, we are done with this. Your supplement contains a lot more scripts. Whenever you have a question related to supervised classification, how do I plot spectral curves? How do I identify GCPs which are misclassified? How do I do stratified sampling? Look in your supplement, you'll find a script. Whenever somebody asks me a question and I can't find a script, I create one and put it in the supplement. So the supplement contains answers to all your questions. So first check that, and you're likely going to find an answer to your classification problem. I've also linked to some references to read these papers specific to classification. These are the selections that will give you some good idea of how people use machine learning in practice on remote sensing.